So the live stream hasn't started yet.
Okay, yeah, I'll just a second. It'll start in a way. Yeah, lives has just started. So I just need one help. So if someone happens to notice either a low volume from my side or some kind of noise, I request you to post it on the chat. Yeah, that way I'll correct it soon because I'll be presenting or coding on some other window and I may not get a chance to look at it that often.
This video, this session will be available on YouTube also for later
Yeah,
on.
yeah, it'll be available on YouTube. So it's currently being streamed. So it'll remain there on YouTube.
Oh, actually, the question was should we do the live coding right now or just watch it and then do the codings later on?
See, ideally that I'm fine with it, but we have some kind of an attendance requirement. If you also want to attend the OPP, that will happen later, right? So,
Oh no, I'm attending the whole thing. I'm just asking should I code along with you right now or just
oh,
watch
okay,
you
okay,
doing
right,
it?
right. So it is preferable if you code along with me, because
Okay.
otherwise it might become boring. But it's up to you, right? So it'll also be there on YouTube later on. So you could also code at that time, but ideally the way we have planned it is I will kind of do a demo of the whole thing and then you can code along. So that is the idea.
Okay.
Also,
Okay.
just to like
Okay, so someone has commented that the voice is low. Is it still low? Is it low for everyone or?
No, so the
It's okay.
voice is fine now.
Okay, thank you.
Only thing is, sir, the availability of YouTube video later on means after this session, this can available or after 2
Yeah, it
p.m.
will be there forever, right? Unless we take it down from YouTube, it's like it's like any other live session. So it will be there. Okay, so yeah, I'll just answer a few very quick questions. See, the assignments will be shared with you. I think you are yet to be enrolled on the course for the workshop. I think once that happens, you will get to know about these assignments and all that. So today it's just an introduction. I mean, not just an introduction. It's an introduction. It's the first day of the session. The rest of the things will get sorted out hopefully as the days go on, right? So yeah, see, for now, what I'm doing is I'm not going to mute everyone, but there's some protocol that we'll follow. Okay, so the protocol that we'll follow is I'll just come to it in a minute, but for now, I'm not muting everyone, right? So please let's try to keep our audios muted most of the time and unmute only when required. Okay.
Excuse me, sir. Sir, I'm
Yeah.
unable to access the assignments, the programming assignments.
Yeah. So we have made them private because the workshop is going on. So we have made them private. Okay. So that will remain private for some time until the workshop ends. All right. So let's get started. I hope the screen is visible for everyone. So yeah. Okay. So what we'll be doing today is we'll be focusing on three libraries that are required for implementing ML techniques from scratch. First one is NumPy, and then Matplotlib, and then SciPy. So as you can see in the slide in front of you, NumPy will be the main focus for today. Okay, and we'll also be doing quite a bit of plotting, and SciPy will do towards the end. Okay, so that's not given that much prominence here. All right, so this is the agenda. So agenda will be as follows. In terms of NumPy, we look at what we mean by vectors, or rather how we look at vectors from the NumPy point of view, how we look at matrices from the NumPy point of view, and how we'll unify these two ideas of vectors and matrices, how we'll unify and look at them as NumPy arrays, and what we mean by NumPy arrays. All these things will be clarified. The fourth thing is sampling from distributions, right? So probability distributions and why it is important will become clear. Okay, that is as far as NumPy is concerned. In terms of the second library, Matplotlib, we'll do broadly three kinds of plots, right? We'll plot simple curves. These are line plots, like y equal to x, y equal to x square, e power x, log x, things like that. So we'll see how to plot them. Then we'll move on to bar plots, histograms, scatter plots, right? So these will be tied to this sampling from distribution, right? We'll tie sampling from distributions and bar plots, histograms, scatter plots, when to use what, all that. And finally, we look at contour plots and 3D plots. These are mostly used to plot functions of two variables, okay? And this will be tied to SciPy, right? So this will be tied to unconstrained and constrained optimization, because a lot of ML, is about optimizing up loss functions and minimizing loss functions, right? So that is how SciPy will come in. So this is the broad agenda for today. So this is a process that we'll follow. So there are going to be 6 collabs, right? I'm not sure how much we will be able to complete in 2 hours. There's a possibility that we might extend beyond 2 hours. I will let you know when it happens. Okay, so the sequence will be, we'll do NumPy first, and then we'll go to Matplotlib, and then we'll come back to NumPy, Matplotlib, SciPy, right? So we'll keep alternating between NumPy. We'll make use of certain things that we learn in NumPy to plot certain functions, certain curves, right? So that is the sequence that we'll follow. As I mentioned earlier, it will be a code with instructor kind of session. It can't be too interactive for the simple reason that the number of people, number of students are too large, right? So the moment we start entertaining too many questions, it becomes tough to stick to the agenda. So there will be code demo, as in I will code and you will code along with me, okay? And after a certain point, I will open the meeting for discussions, okay? At that time, you can ask your questions. To the extent possible, please refrain from asking questions in between, right? So there'll be a clear pointer when I will say that it is time for Q&A. At that time, you can raise your hand, and I'll maybe take 2 or 3 questions. Again, I'm restricting it because we can't do justice to everyone. So any other questions can be taken offline, or we can discuss it separately, right? So that's the type of session. And most importantly, the collabs are present in this URL, so you can now go and check out this URL. So for all 3 days, whatever collabs we are going to work with, we'll share it here. And I request you to spend, say, some 10-20 seconds going and checking this out. tiny.cc/mlt_workshop. Okay, so I think someone has posted the link also. Okay, thanks. Yeah. So for those, okay, so you have that. I know that you have another workshop at 7, but what I'll do is 5 to 7 is in terms of attendance. If you're thinking about attendance and how it will be recorded, the official session is from 5 to 7, but I may go beyond that, right? So that whatever overflows it's okay. If you don't attend that, it's okay. It'll anyway be there on YouTube, so you can watch it later. Okay, so what is important is, from the attendance point of view, is this 5 to 7. Okay, so but I don't want to restrict it to that. In case it goes beyond that, then we'll see. Okay, so is the protocol clear? What process we are going to follow? So the Okay, thank you. Right, so we'll get started. Let me just show you the workshop, that folder, right? That drive folder. That link will tiny.cc/mlt workshop will actually take you to this particular folder having 6 collabs, right? So these 6 collabs are what we'll be working on, and I have opened the first collab here. Okay, so just give me a second. Yeah, so now what we'll do is we'll get started. So first things first. So a brief introduction about these 3 libraries, right? So NumPy, Matplotlib, SciPy. So these 3 were created kind of in the early 2000s, right? So 2005, 2003, 2001, and all 3 are open source. Their current versions are as follows, right? So it's 1.223 for NumPy, 3.6, and 1.9 for SciPy, right? So these are some brief history of when they were created, right? So they are not very old. If you think about it, they are hardly 20 years old, right? So not even 20 years old. So what is our use? Our use for these 3 libraries is given here in the third column. NumPy will be mainly for linear algebra and operations pertaining to it. Matplotlib will be basically for visualizing data and all the models that we built, and SciPy will be for optimization. Okay, so these 3 tools or libraries are obviously, far more powerful than what we'll be seeing of them. But what I've listed here is our use case, right? So for our use case, this is all that is required, and this itself, if you think about it, is quite heavy. Okay, so one final point before we get started with the coding. See, this is going to be a very beginner friendly workshop, or that's how we have planned it. So we will start from scratch. Okay, so in case you already know NumPy, perhaps you might be bored. Okay, so this is unfortunate, but if you already know NumPy and if you know how to plot stuff in Matplotlib, and if you already know how to optimize functions in SciPy, then this could be boring, but you could stay along, for reinforcing your concepts. That is still a possibility, right? But this will be starting from scratch. So we'll be starting from very basics and quickly move to more advanced topics. Okay, so that's our hope. Okay, so first thing is the idea of vectors. So I think we should have kind of done this even before the MLT course began. But anyway, so we see this idea of vectors in take multiple forms, right? Depending on what the context is. Right? So for example, when we look at a data set, right? When we go out into the field and collect data in a very statistical sense, data is what each data element or each data sample, as we call it, is very practical, right? So for example, we might be analyzing the heights and weights of individuals in a city, right? So height is a feature, weight is a feature. It's something extremely practical. So you could say 160 centimeters is the height and 75 kg is the weight, right? So at that level, we are talking about a sample or a training example or whatever, right? So there, the notion of a vector is very practical. We have not yet entered the domain of vectors. We are still dealing with measurements, right? Observations. And suddenly we start talking about vectors, right? When you come to MLT. So there is some process of abstraction happening, and this abstraction is done by this thing called a feature vector, right? So you put all the features together, you list them down one after the other, and you turn it into a feature vector. So the moment you do this, moment you make this transition, what you do is you open up the entire world of linear algebra for machine learning techniques, right? So the moment you say that here is a training example, here is a sample from my data set, and I'm going to represent it as a vector, then you open up a lot of things. So what are these things that you open up? First thing is that you get the ability to look at your sample geometrically and algebraically, right? So geometric meaning vector has some magnitude and direction, right? So where does this come from? This is not inherent in your idea of a sample or your idea of a training exam, right? So this direction and magnitude, these things come because you have turned it into a mathematical object and you start studying that, right? So direction, magnitude, and the whole idea of a data point, right? So you would have often observed, right? And you might have even wondered, so what is this data point business? What does it have to do with the feature vector? What does it have to do with the training sample, right? We use these terms interchangeably simply because when we say data point, we are referring to some kind of a space, right? Some vector space where this vector is living in. Okay, so that idea comes in. And finally, what we are today interested in is this computational angle. So as far as a computer or a machine is concerned, the vector is just an array, right? So in Python terms, it's a list. So list is what? A sequence of numbers. Vector is a sequence of numbers. So as far as a machine is concerned, your sample or your training example is just a sequence of numbers. Okay, so that is where we are going to start. And pictorially, we can think about a vector as this kind of a sequence, right? A list. Okay, so with that introduction, we can get started. With coding. I hope all of you are able to access the collab. So for this alone, can someone confirm? Are you able to access this first collab? And
Yes, sir.
okay, right. So for those who are not able to, this tiny.cc, can someone paste the URL if you already have it copied in your clipboard? Yeah, thank you. Okay. So vectors is what we'll be doing. Okay, so let's get started. First thing is easy. It's just you just have to import, right? Import along with me stage, right? So import numpy as np. So there are a few tricks which will make our life simple. Whenever you want to run a cell, right? So if you are not used to Colab, then each of these things is called a code cell. And if you want to run it, you could either press the play button. If not, you could do control enter, right? So if I do control enter, then first, if your Colab is not yet connected, it will get connected. Some memory and storage will get allocated. And once it is initialized, you will be able to run your cell. Okay, so what I'll be doing is I won't go and press the play button every time. I'll just do control enter. So you won't see me pressing the button, but I'll be doing control enter, or there are other possibilities as well. So control enter is to run one cell. Right, so there is control plus F10 also does the same thing. Control plus F9 is also there. So control plus F9 will run all the cells, right? So it will run the entire collab. Okay, so these are some things you can get used to. Right, so yeah, first thing is we have two vectors here, and first question we ask is how can we represent these two vectors in Python? Okay, so forget all about NumPy. We have imported NumPy, but even basic question is how do I represent these as objects in Python? And the answer is also given here using Python lists. So what we'll do is we'll quickly go ahead and add these two vectors. So we'll define these two vectors. So this is 1, 2, 3. And this is 4, 5, 6. Okay, so these are two Python lists, and let's see how difficult or how easy it is to create this new vector z, which is the sum of x and y, right? So first thing is you create an empty list, and then you kind of iterate through these three elements in your vector, and you add x of I and y of I. Okay, and then you append this, right? So simple operation. So you're done, right? So this is a simple code to add two vectors and create another vector in Python. Okay, we have only used lists here, but we'll see that this is, though it's kind of easy to do it, it soon becomes quite complicated when we want to do more complex operations on vectors, right? So in order to make life simple, we introduce what is called a NumPy array, right? So this vector can now be expressed in NumPy as, okay, as simple as this. So you have just created your first array. Let's see how it looks. So in another tip when it comes to Colab is, if you type an expression here, any kind of expression here, and run the cell, whatever is the value of this expression, that will get printed here. Okay, so you don't need to necessarily do a print of x. It's also fine if you do a print of x, you'll get 1 2 3. But what we'll do mostly is we'll just write down x, and then the output area will show you what the value of this expression x is. Okay, so this is again another shortcut in Colab.
Karthik sir, may I interrupt you?
Yes, yeah.
See, the one always I had a doubt is npy.array. We put it in that square bracket for the list. That simple bracket, does it denote something? Is it a must for us to do it, or will it throw an error, sir?
You mean this bracket, the flower bracket, the round bracket?
Yes, sir.
Or
Yes.
the round
That's
bracket is essential, right? So you are creating your, so np.array is
oh,
you can
okay.
think about it as a function, and you are creating an array out of a list.
Okay. Okay. Thank you, sir.
Yeah. Okay, so this is how simple it is to create a vector. Don't worry about what we mean by an array now. For now, all that you need to understand is, if you want to create a vector in NumPy, then this is how you do it. Okay, so this is the first step. Now we'll see how vector addition becomes extremely simple the moment you do this. So again, code along here. We have x as 1 2 3 and y as dot array of 4 5 6. Okay, so this is the second vector. Now all that you need to do is z equal to x plus y. Okay, so you get the sum of these two vectors, right? So compare and contrast this with what you did earlier. So the main difference is, here you have to do it element by element. You had to explicitly loop over the list, right? So note that in native Python, you had to explicitly loop over the list, right? You had a for loop and you had to sum element by element. Whereas in NumPy, what NumPy does for you is, it does this looping internally, and it does it far more efficiently than what native Python will do. Okay, so this is vector addition in NumPy. So you have defined two vectors, you have added them. Okay, so let's move on, and this will require some time. So yeah, so the next thing is what is called element-wise product. So this is called Hadamard product in math. So let's do this element-wise product again. np.array 1 2 3 and np.array 4 5 6. This creates two vectors for you, and x into y, the usual multiplication symbol, will give you an element-wise product. Okay, so 4 10 18, right? So it has multiplied these two vectors element-wise, as simple as that. Okay, next thing has to do with scaling a vector. Okay, so scaling a vector is nothing but multiplying it by some constant. Okay, and in terms of geometry, this has the effect of making it longer or shorter, or changing its direction if the constant that you multiply it is negative, right? So how do you do scaling? Again, very simple. You first define the vector 1 2 3, and y is nothing but 3 times x, and you have scaled your vector 3 times by 3, by a factor of 3. Okay, so I'll just pause for a moment here, and are there any questions at this stage? Okay. are no questions, let's move on to.
Sir, one question. Do we
Yeah.
have to make X and Y every time, like convert them into array every time, just like you have converted them again when you have multiplied with 3? You have converted into np dot array again when you have added them.
Okay, that's not necessary if you're dealing with the same vectors. So I'm just doing it for completeness sake. But if you have already defined x and y somewhere else in your collab, right? So for example, you have already defined it here. X and y have been defined. And if you're dealing with the same x and y, then you don't need to do this lines 1 and 2 again. Right? So you can just go on with whatever x you have. Okay, so any other questions? Not really. Move on to.
Yeah. Sir, is NumPy contains internally different methods for adding, sir? Looping, like looping?
Yeah, so we'll come to that. I'll not discuss it in much detail because, for one thing, I am not an expert when it comes to the internals of NumPy. So that is one reason. Second reason is, for our purposes, we'll be mostly concerned with how we can express mathematical expressions in NumPy and use it for MLT, right? So what you're asking is a very important question. We'll very briefly touch upon it in a related slide, right? Next slide is really based on that. Okay, so I'll just come to that question that you asked. So when you multiply a vector, say 1, 2, 3 with 2, this is what scaling is, right? You are multiplying a vector by a scalar. So here the vector is 1, 2, 3, and you are scaling it by 2. What NumPy actually is doing is, it is kind of, right? I'm saying kind of, so you should take it in that sense. It's creating these copies of that scalar. Okay, it's creating 2 copies of scalar so that it can multiply these 2 vectors element wise. Okay, element wise multiplication we saw, right? You multiply each element of one vector with the other vector, and NumPy kind of does it well. Now, what scaling is, you can understand it as this kind of an operation where it stretches this scalar to the length of the original vector which it is scaling. Okay, and then it does an element wise multiplication. Okay, so this principle, the principle behind this is called broadcasting. Okay, it's, if you want to understand NumPy in detail, you need to understand what broadcasting is. But at our level, it's enough if you know the basics. So broadcasting typically comes in when you want to do an operation with multiple vectors, right? Either with a vector and a scalar, or with 2 vectors but which are of different sizes. Okay, so here this vector has size 3, this is a scalar. Okay, so how does NumPy figure out what to do with a scalar and a vector? So this is given by certain rules called broadcasting rules, and roughly it is enough if you understand that it does some kind of stretching of the scalar along the direction of the vector and then does element wise multiplication. Okay, so as I said, this is only a conceptual explanation. This is not exactly what happens in NumPy. So to your question of what happens internally, this operation of multiplying this vector by a scalar is actually more efficient than multiplying this vector by this vector, even though both of them produce the same result. Okay, so yeah, so what NumPy does is it internally has a looping structure. Okay, so this looping happens in C and not in Python, which is the reason why NumPy is fast. Okay, so in Python, if you notice, we tried to add 2 vectors. We used a for loop. This for loop was in Python itself, right? Whereas NumPy also has to do some kind of looping operation because all element-wise operations are ultimately
We can't hear you.
Sir, you're not audible.
His voice was breaking, right?
Oh, it's not. He's not audible.
Hear him at all.
Even before, his voice was breaking. Is it?
Yeah, there was a bit of static.
Hello, sir. Sir, are you audible? Hello.
सन्नाटा क्यों है भाई?
Hello.
Sir, you are audible.
You're audible.
Yeah, so there's a power cut at my place. I'm sorry. So I'll try to hope it comes back. So I'm currently on mobile data. Let's see how long it holds up. So is my screen is still visible or?
Broadcasting page.
Okay, thank you. Right. So yeah, let's continue. Yeah, so that is what broadcasting is, right? Broadcasting is NumPy's way of figuring out how to deal with two vectors when some arithmetic operation is involved, right? So it's enough if you understand this much. So let's go back to scaling where we left. Okay, so we understand what scaling is. The next thing is element-wise function, right? So what this is actually, we first reconnect. Yeah, so sometimes you might want to do element-wise operations on a vector. So for example, scaling is one such operation, right? So what is scaling? It multiplies each element of your vector with some constant k, right? That is what scaling is. So you can look at scaling as element-wise multiplication, or applying this function f of x equal to kx to every element, right? So likewise, you could kind of extend this in NumPy to other functions as well, right? Why stop with scaling? Let's say we want to do x square and we want to do it element-wise, right? So let's define this new array now, or this new vector of 1, 2, 3, 4, and you want to multiply each one of these with itself, right? Each element of this vector with itself, right? NumPy is as simple as this. Okay, so x square and you are done. Okay, so what it has done is it has multiplied it with itself. So this is actually kind of equivalent to this. Okay, so we have done is x square. I hope you all get what has happened. So this is one example of an element-wise operation. Each element of the vector was scaled. Let's look at one more. Let's do now this log of x on each element of the array. So let's define this vector of 1, 10, 100, 1000, 10,000, and 100,000, right? So once we define this vector, what we need to do is take the log. So np.log is how we do it. Since the base is 10, we use np.log 10 of x. Okay, and let's just run it. We see that we get log to the base 10 of this array, right? So log 1 is 0, log 10 is 1, and so on. Okay, again, what it has done is you have applied a function f of x, but you have applied it element wise. You have applied it on each element of the array or each element of the vector. Okay, one more example. Let's now do it for log to the base e. Now our array is going to be 1 e square e cube, right? So it's 1 np dot e square np dot e cube, right? So E is this popular constant that you're all familiar with, and to access it using NumPy, it's np.e, right? So that's how you do it. And by default, np.log will give you log to the base e, right? And you can run this, you'll get 0, 1, 2, 3. All right, so that is np.log, np.log10. And earlier the function that we looked at was simply x square. Okay. And next, what we may have to do is we may have to add a constant to each element of a vector. Okay, so you have vector 1, 2, 3. You might want to add, say, the number 5 to every element of the vector. So let's do that now. And if you have noticed what has happened so far, you define C as 5, then plus C is all that you need. NumPy will kind of figure out that it has to broadcast. Again, I'm using this term broadcast. NumPy will know that it has to broadcast the C in such a way that it gets added to each element of the vector x, right? So slightly more involved example. So how do you do 5 into x minus 2? This is again element wise. Again, if you have followed what we have been doing so far, first create the vector minus 1, 0, 1, 2. Okay, and y is 5 into x minus 2. So let's print y, see what we get. Okay, so 5 into minus 1 minus 5 minus 2 is minus 7, so on, right? 5 into 0 minus 2. So it has actually done this whole thing element wise. So the main lesson that we have to learn here is that the translation from mathematics to NumPy is very straightforward. Okay, so when you say 5x minus 2, it's actually as just like writing this 5x minus 2, instead of a multiplication symbol, you have a star, which is what multiplication stands for in Python, right? So conversion from math to NumPy is so straightforward, and that is the main point that we wanted to make with these 4 examples, right? So any questions about this element wise operation? Okay, right. So next we move on to the next idea, which is kind of the most important idea. Yeah.
So is there any limit?
Yes.
Like when you are using broadcasting, you said when there will be dimensional differences, it will internally try to stretch it. So means there are some limit. Is there any limitations when we can see, means be aware of that? In this case, broadcasting won't work. For the means
Yeah,
if there
yeah.
is
So there are
inherit in
some
dimension.
correct. Yeah. So there are some rules for broadcasting. We will study those rules not in too much detail. We'll get back to broadcasting and we'll look at matrix operations. Okay, so there the rule will get slightly better or it will become clearer, but we'll not explicitly define the rule. That is left for you as say reading exercise at the end. Okay, but there is a rule, a very well defined rule is there. So for our purpose, it's not important at this stage. Okay.
Sir?
Yeah.
There was one example where you used underscore with 10,000 and above number 10,000 and 1 lakh. So is it necessary to use the underscore or it's just for the notation purpose?
Yeah, so it's just to make things more readable. That's all, for readable code. So this 10,000, we usually use this comma, right? So when we write 10,000, 10 comma 000, so it's equivalent of that in Python. That's all. There's no.
Okay. Right. Okay. Thank you.
Okay, so that is regarding element-wise operations on vectors. Now we come to one of the most important aspects, is the dot product. So we want to find the dot product of these 2 vectors. Let's first create these 2 vectors, 2, 3, 4, and vector x, vector y is. Okay, so these are 2 vectors. Now there are 2 ways to get the dot product, and we'll mostly stick to one of these 2, and that is as follows. So x np dot x comma y is one way. Okay, so NumPy provides one method called dot, which gives you the dot product of x and y. Okay, so this will turn out to be minus 60. You can verify it later. There is also another method that, not method as such, but an operator which NumPy provides. It's called the at operator. Okay, so this also means x dot y. Okay, so this is what we'll be following. At it stands for multiplication among vectors and matrices, right? When you come to matrix, you will see when we go to the matrices section, you will see that at corresponds to matrix multiplication. Okay, but when we have vectors on both the sides, it just reduces to the simple dot product. Okay, so this is a very important operator, and we'll be using it frequently all through today and tomorrow, day after. All right, so that is the dot product. You can forget np dot dot, but it's good to remember if in case you are reading code written by someone else in NumPy, x at y is what we'll be using. Okay, so that is that. Next we come to this part.
Sorry,
So,
sir.
yeah.
So I didn't understand why we will use x at the rate y rather than np dot. Can you repeat that?
So there are preferences, right? So for example, if you look at code, so there could be two reasons. I'll tell you only one. The second reason is something that we'll all have to research. I don't know how fast x at y is compared to np dot x comma y, right? So that is something that I am ignorant of. So are they the same in terms of efficiency? Is something I don't know. But in terms of notation, I find x at y kind of easier because it unifies matrix multiplication, the notation for matrix multiplication and that of vectors, right? So when will you use np dot x comma y? So you'll use it when you are explicitly dealing with two vectors, right? So there np dot is probably more preferable because you set the context straight. Okay, so if I just write x at y and I don't know anything about x and y, then they could be matrices. So if you're reading the code written by someone else, you could be fooled into thinking that x and y are matrices and not vectors. Whereas here, maybe it's more clear that it has to be two vectors, right? But again, this is a very loose explanation. So at this stage, I would say it's a matter of preference. Okay, so.
Excuse me, sir. Why you have not taken it X transpose?
Good point. So see, when it comes to NumPy, the vector is an array. Okay, so vector is an array, but it's what is called a single dimensional array. So we'll get back to this, but there's no concept of column vector, row vector that we actually deal with, right? So that's why if you notice, we have two formulas here, right? X transpose y, x dot y. So when you say x transpose y, you are implicitly referring to x as a column vector, right? So that's what you're doing. Yeah, sorry. X dot y is more closer to x at y. Okay, so we'll come to this. I'll touch upon what we call the dimension of a NumPy array. So NumPy vectors as such, there is no concept of row vector, column vector. So if you do x transpose, for instance, I'll probably show you this part. So if you do x transpose, you will get x itself, right? Because for a NumPy vector, there is no concept of transpose. Okay, this will become clear to you when we discuss what we mean by the dimension of an array and all that. Okay, for now, it's enough if we are able to understand that x at y is the dot product. Okay, so that is with respect to dot product. As I said, the convention that we'll follow is x at y. Okay, so which brings us to vectors of zeros and ones. So when will you use this? You will use this typically when you want to create, initial vector in initial weight vector, right? So your weight vector in many algorithms are 0 vectors, right? So you start with W equal to 0 and then you proceed. A vector of ones, some of you have taken who remember the content will realize that we use it in, say, SVMs in some areas, right? So typically when we want to sum a vector, we say it's alpha transpose 1. Okay, so these are things that we do quite often. Okay, so how do we do this, right? How do we create 0 vectors? A very simple command, np.zeros of how many zeros do we want? What's the dimension of the vector? So 1, 2, 3, 4, 5, right? So we want a vector in R5, a 0 vector in R5. So that is called 0. And ones is likewise very simple. We just need 5 ones, right? So that is a vector. Okay, so 0 and 1 are the 0 vector and the vector of ones. Next, let's quickly move to the norm of a vector. Norm is related to the length. Okay, so typically we go for the L2 norm, right? So L2 norm is square root of sum of squares, the components, right? So how do we do that in NumPy? Let's first define the vector, and then there are two ways to do this. One is if you want the L2 norm, then you could do x square. X square will do what? It'll do 1 square, 2 square, 3 square element wise. And then you could do what is called np dot sum of x square. Okay, so let's first do this and see what happens. So what x square is what? 149. np dot sum will sum the elements of the vector. It will give you 14. But this is not the norm. Square root of this is the norm. So do something as simple as this. Okay, so that will give you the L2 norm. Okay, this is one way of doing it. But NumPy thankfully provides method for norms. So you have to use what is called the lineage module. Okay, so np.lineage.norm of x. That will also return the same thing, 3.74. Okay, so np.lineage.norm is going to return by default the L2 norm. Now, what about the L1 norm? If you want the L1 norm, you have to just enter the norm that you want. So if it is 1, this will return the L1 norm. If it is 2, it will return the L2 norm. If you don't enter anything, by default, it is going to return the L2 norm. So far, are things clear? Okay. So
Yes, sir.
final part is the shape of a vector and the dimension of a vector. We'll expand on these two notions, but for now it's enough to understand that the shape of a vector will return this called a tuple, right? A tuple with the length of that vector, right? How many size of the vector, length, whatever you want to call it. So how many components does it have? It has 4 components. So it'll return that. In addition, there is another thing called the dimension of a vector. So, or rather of an array has a dimension, and in the case of vectors, that array dimension is 1. Okay, so that brings an end to the first collab. I hope you have some idea of vectors now. And can we move on to the second one?
Hello, sir.
Yeah.
So why we are using not using np.size, sir?
Good point. So see, everything is not a method of the NP, NP module, right? So some are methods, some are attributes of objects, right? So for example, X is an NumPy array and shape is one of the attributes of X, right? So shape np.shape, so you can test this out. What I'll say is attribute error, oh, here it's there. So Sometimes it will be there, sometimes it won't be there, but it's okay. So good point. So there are two things, right? One is here shape is being used as an attribute of the NumPy object X. Okay, it so happens that shape is also one of the methods in the NumPy module, but this is not always the case. Okay, so for example, there is np.sum of X. You could also write x.sum of. Okay, so there are cases when some method of NumPy module, it is also a method of the NumPy array object, but this doesn't extend to all cases. So whenever you have an attribute that is present for an object associated with it, we will prefer to use that attribute instead of saying np.shape. Okay, so if I can do x.shape, I wouldn't want to use np.shape of X. Is that satisfactory?
Hello, sir.
Yeah.
Sir, what is the dimension here? Sir, since better is 4 dimensions, so the dimension should return 4, right? But it is 1.
No. So that's what I have written here, right? So dimension is different in NumPy and it is different in math. Okay, so what we are talking about here is the NumPy array dimension. So again, I'll expand on this when we study matrices. It will become very clear. But for now, you have to understand that vectors are one-dimensional NumPy arrays.
Okay, sir.
Okay. Yeah. So we'll move on now to plotting. Before we move on to plotting, I just want to quickly talk about this. So there's a quick summary slide. So notice how you have math expressions on the left column here and their corresponding NumPy equivalents. So you can notice how closely related the two are. So x plus y in mathematics is the same in NumPy. Element-wise product is the same. Dot product is very similar with just one at here. And if you want to do something like ax plus b, that is also quite similar. This is np.zeros, np.ones, and if you want to find the norm, this is how you do it. So this is a quick summary of what we have done. Okay.
What is the significance of p here in norm?
P is what is called the order of the norm. So there are different kinds of norms, right? So L1 norm, L2 norm are two norms which we are usually which we are familiar with, right? So there are other kinds of norms also. So there are, you could define an L3 norm, for instance.
Yeah, okay, I got it.
Okay, so let's start plotting now. How do we plot? So let's first get hold of so the slides also will be shared. Import whatever is needed. So import NumPy as NP is something you must be familiar with by now. Import matplotlib.pyplot. Okay, so here within the matplotlib library, there's one module called pyplot, and we are going to import that as PLT. So we are going to have another name for it. So it's called an alias. We'll, instead of every time referring to pyplot, what we'll do is we'll refer to it as PLT, right? PLT. Okay, so that is, we've done this. Next, what I'm going to do is kind of not very important for now. I want to set my size of my plots. Okay, so the way to do it in NumPy, so I want to set it as 8 cross 8. Okay, so usually the plots that you get look small, and I don't want to deal with small plots, so I'm increasing the size. And one way is to fix this in the configuration, right? So these are some configurations that you're adjusting. Okay, so another thing that I want to configure is the size of numbers, labels that appear on my plot. So I'm not exactly sure what this is. Font dot size, right? So this is font dot size, and I want my font size to be, say, 10. Okay, so you can play around with this and see how it affects your plot. But for now, I'm going to set these as defaults. Okay, so it's running. Someone is asking, where can we get these collabs? You have to, there was a link that was shared with you early on. I hope you have access to that. Yeah, thanks. So, right, moving on. So, how do we plot, right? So, in order to plot, what we need is a set of x values and the corresponding y values, right? So, this is how we plotted during school days. If they are asked to plot a line, then we have 2 points and then corresponding y values we take, and then we draw a line through them. If you want to plot more complex surface, more complex curves like say a parabola, then you take 3 points and draw a smooth curve through them, right? So first we need to generate a list of values for x, right? And the way to do that in NumPy is this method called linspace. Okay, so what does linspace do is this, right? So it takes 2 endpoints between which you want to generate, equally spaced points. So between 0 and 1, I want 3 equally spaced points, endpoints inclusive. Okay, so we have 3 points that are equally spaced between 0 and 1. Now let's change this number of points to 4, then you have 0 0.33, 0.661, right? Equally spaced, and there are 4 points. Now if you go for 5, then you have something like this, 0.25, 0.5, 0.75. Finally, if you want 6 points, then it's something like this, right? So what this does is it gives you a certain number of points in the interval a comma b, which are equally spaced. Now, why is this useful? This is useful for plotting because at each of these intervals or at each of these individual points, if I have a y value, then I can draw a smooth curve through these values, right? So that is how I'm going to plot. So yes, so what I'll just do a quick demo here. np.linspace. Let's say instead of 0, 1, we do 0, 5, and we sample 20 points, right? Endpoint inclusive. And let's see how it looks. Okay, so this is how it looks, right? So some 20 points. The only catch is that they're all equally spaced. Okay, so that is what you need to keep in mind. Okay, now we have everything ready to start plotting. So let's take up the first plot. We are going to plot the simplest of curves, which is the y equal to x curve. It's a straight line. So we have been asked to sample 10 points. So let's do that. np.linspace between 0 and 1, sample 10 points, and then define y equal to x. Okay, so the method to plot is plt.plot x comma y. So right, so let's done, and you have the plot. Okay, so let me just go back and change the font size. Apparently it does, font size is not reflecting. Okay, I need a slightly larger font size, so let me make it 15 and run this again. Okay, that's better, right? So what we have now is y equal to x, as simple as that. Okay, so one more trick that you need to know is this, the output of the last line, right? If you remember what I told you, this is the output of the last line in the cell. Sometimes you might want to suppress this output, right? So you might want to suppress the output of the last line. Okay, so what you do is you add a semicolon and then matplotlib and Colab will suppress it, right? So if I run this, you'll notice that this particular line doesn't appear. Whereas if I run it without the semicolon, that line appears, right? Sometimes that line can be a nuisance, that output. So especially when you plot things, so I suppress it usually. Okay, so that is simple plotting. Any doubts with regard to curve 1? Okay, so no doubts. So we'll move on. Curve 2 is again simple. Only thing is we are changing the interval np dot lin space of -5, 5. We are sampling 20 points. And we are plotting y equal to 5 minus 3x. Notice how the element wise operation comes in handy here, right? So we define it as though x were a scalar. Okay, actually x is a vector, but we define it as though it is a scalar. And because of the element wise operation, this gets broadcast to all values of x, all the components of x. Okay, so same protocol for plotting plt.plot x comma y. Yeah, I want to suppress this output, so let me do that. The interesting part is that we have to add a title for this plot, which has the equation of the curve. So the title is done using plt.title. Okay, and y equal to 5 minus 3x. So that's the title. Some unwanted text is coming here, so I'll suppress that. Okay, so that is the plot of 5 minus 3x, y equal to 5 minus 3x.
Excuse me, sir.
Yeah.
Why do we suppress that?
So it's just for convenience, right? So if I don't suppress it, I have this output of the last cell, of last line of the cell. It's kind of I find it annoying, so I suppress it, right? So that is the only reason.
Okay, thank you.
Okay, no other. Okay, so curve 2, curve 3 is interesting because you will understand plotting slightly better. It's a parabola, very simple parabola. So x is between -1 and 1. Let's say 5 equally. So we have to try it out with different number of samples, right? First is 5 equally spaced points. So let's do that. So I have taken 5, y equal to x square, again element wise operation, plt.plot y. Okay, plt.title y equal to x square. Let's first run this and see what happens. Okay, first of all, this caret sign is there. So usually if you enclose it in dollar, that caret will go away and it will become power, right? So it's, for those of you who are aware of LaTeX, that's how you do it. So far so good. But if you go and visualize the plot, you see that you see something weird, right? So this is not at all smooth. So why do you think this is not smooth? Can someone tell me?
Because we are taking
What's
fewer
this?
points, so it's just joining them with straight lines.
Right, so we are taking fewer points. So let's try to increase the sample. Let's try 10 points. Okay, still there is this kind of piecewise linear nature, which we don't want. Let's try 20. Smoother, but still you can see this linearity coming in. So finally, we take 50, then you will see that it's, at least to our human eyes, actually this is, if you think about it, you will realize that there are actually how many 50 lines here, right? So for the case of 5, there were how many lines? At 1 line, 2, 3, 4, right? Okay, there were 4 lines. Now in the case of 50, there will actually be how many? 49 lines. Okay, so but because of the limitations of our eyes, our sight, right, we can't go and penetrate what's happening there. So it looks smooth, but that's what we want. As long as it appears smooth to our eyes, that's enough, right? But internally, what's happening is you have some 50 lines that are so close to each other that it looks smooth, right? So this is y equal to x square. Okay, that is curve 3. Now, yeah, so curve 3. Any doubts about the previous curve? Because this is
Yeah, one question here.
Yeah.
Is that the number of 50 interval is there? So this is how will I come to know that which one is the optimized number? Because curve can be anything. It can be sinusoidal or something. It is hit and trial. I can increase the number of partitions to see that where the curve is going to smooth. Or is that any automatic way that he will decide that matplotlib that at this particular interval it's automatically going.
Okay. To my knowledge, I don't know if there is any such predefined sampling frequency.
Okay.
I think it is hit and try, right? So for example, this won't work for, if I'm right, this won't work for say -100 to 100.
Yes,
if
yes,
you want,
yes,
right?
yes,
So
yes.
look, maybe it works. I don't know, right? So
because it is the graph is very compressed. That's why. If it will go bigger, then it may not.
Right. So it is, as long as you choose points which are dense enough, it's okay. But I think it's hit and try. To my knowledge, there is no predefined rule.
Okay.
Okay, so that is y equal x square. Plotting.
Sir, I have a question.
Yeah.
So what if I don't want to include the endpoints?
Okay, so there is an option not to include the right endpoint. So if you look at np.linspace, if you do question mark, you will get you will get to know what all can be done. So returns evenly spaced numbers over an interval, returns these many evenly spaced samples calculated over the interval. The endpoint of the interval can be excluded. I don't think the start point can be excluded. Okay, so we'll come to that also. If you want to exclude the start point, one practical way is to say start with something very small, close to -1, say -1.0001. Let's say you don't want to include -1, but you want to continue. No. So what is to the right of -1? 0.99, right? This is close. To the right of -1 is 0.99. Is that right?
Yes.
Okay, so practically you would do something like this. Instead of starting at -1, you will start slightly to the right of -1.
Okay, sir. Thank you, sir.
Yeah. This is a good question because we'll come to that when we do 1 by x. Right.
If we remove 50 from here, right, then I'm getting the smooth curve here. So what are the partitioning here? Just
remove 50, is it?
Yes, sir. -1 to 1. And if I'm doing that, so yeah, we are getting this smooth curve. So how much partitioning is being done here?
Yeah. So you can look at the shape of x. So that will give you, so x by default it is doing 50, right? So np.linspace by default it's 50. I don't know. Let's look at it. np.linspace. What does it say? It says okay, by default itself it is 50. So that's why you are getting the same smooth curve. Right? So
okay.
Right, so yeah, that is.
Will it depend on like -1 and on the default value?
No, I don't think so. So let's try say np.linspace of 0, 100 and click on the shape. So if you try to find the shape, it is still 50, right? So it is independent of what the endpoints are. Okay, so yeah, just one question.
Sir?
Yeah, just one announcement. See, my power supply is still to resume. I have around 1 hour 12 minutes remaining according to my system. So if I get logged out suddenly, it means that I have run out of power. Okay, so just an announcement. I hope to finish at least till 7 before that. Yeah, please go on.
See, when you typed in, you wrote linspace shape and a question mark. So when you type in question mark, it gives us a help in the right side, is it? Anytime?
Yeah. So it gives you help for the particular method that you want to. So for example, if I want to know what all I can do with plot, right? So with plt.plot, you can do all these things. it gives you, as it says, right, the signature of the function and the doc string
Okay.
associated with it.
Thank you so much, sir.
Sir, I can use a PLT dot shape or NP dot shape. How to check this, please?
NP dot shape, right? The shape is something that is an attribute of a vector or a NumPy array, right? It has nothing to do with the plotting facility.
Okay.
Okay. Yeah. So at this stage, I'm sorry, I'll have to move on. So we'll come back to questions slightly at a future date. So next is again important when you. So this is about coloring the plot, coloring the lines that you are drawing. So first thing is we have to plot two lines, but these are slightly different, right? So it's not simply y equal to x or y equal to 3x minus y, but these are like weird lines. They are parallel to the x and y axis. So let's see how we do that. So here what I'll do is I'll not do linspace because it will become clear. What I'll do is instead just do 0, 1, 2, 3, 4, 5, 6, right? So that is my range for x. For all these values of x, the y value is y equal to 3. Okay, so I'll first do that. X comma, so y equal to 3, right? So instead of doing np.array of so many things, I'll probably do np dot ones of 6 or 7, right? So I hope you all get this. There are 7 elements here. So I need 7 threes. Okay, so I just do 3 into np dot ones of 7. And I just plot this first. Okay, so this is the line y equal to 3. Okay, so 0 starts here. So we have done one part. Now, similarly, what we can do is we can fix y here as np dot array of the same 0 to 1, 0 to 6. Okay, the x corresponding to that is 5, right? So that is 5 into np dot ones of 7. Let's plot this. Okay, so it gives some default color, blue and orange. We need to change that. So the y equal to 3 line should be green, right? So should it be green? Yeah, first one is green. So this has to be green, and this one has to be red. Okay, so we do that. We have the color, but we don't stop with that. We also have to have a title. So let's title the plot as y equal to 3 and x equal to 5. So I'll suppress the output with a semicolon. Y equal to 3 and x equal to 5. So y equal to 3, x equal to 5. But we are not done yet. We have one more requirement, which is a legend. Okay, so it's simple. You just need to do plt.legend and it will add a legend. But you need to tell your plot what is what, right? So you have to label each plot. So I label this curve as y equal to 3 because that is what it is, and I label this as x equal to 5. So notice what happens when I run this. Okay, so there is some mistake that we have made. Okay, so I ended up labeling the wrong thing. So I have to label this, not that. Okay, so okay, okay, for some reason the legend is kind of not coming where it should.
You have to write the label.
Oh, right. Thank you. I didn't write the label. Okay, so yeah, thanks for pointing it out. So what we have done is, so let's just quickly go over it. So x and y are the x and y for this particular line y equal to 3. We have plotted x and y. In addition to it, we have colored it green and we have labeled it as y equal to 3. So that is green y equal to 3. And then we have done again x comma y and we have labeled it red, okay, and colored it red. So Is that fine? So this is how you label a plot, how you title a plot, how you add a legend to a plot. Okay, so I hope there are no questions here. If not, we can move on. Okay, so plotting in Matplotlib, I just want to present this slide to you for subplots. Sometimes what happens is you might want to represent multiple plots on the same canvas, okay, but not on the same plot. So what we did in the previous example was, for whatever reason we wanted to compare y equal to 3 and x equal to 5, these two curves. So we plotted both of them on the same figure, right? So same Matplotlib figure. But what happens is, it could happen that you might want to plot 4 different curves, but on separate plots, right? So in such a case, we have what is called a subplot. Okay, so this is how the syntax is. So plt.subplot, you want a 2x2 plot. So this is a 2x2 plot, 4 subplots. The index of the first subplot is 1, index of the second is 2, 3, and 4. Okay, so every time you want to plot something in this region, you will use this plt.subplot of 2 to 1 and then do the plot. Likewise, you will do it for all 4. It will become clear when we do this example. So let's get started. We have to plot 4 curves, ln x, e power x, sin x, and 1 by x. Okay, all are having different ranges. So let's first go ahead and do ln x. So my linspace will be, say, 1 divided by e square comma e cube. Okay. And let's keep the default 50. Okay, so let's not mention the sampling frequency. Y is nothing but np dot log of x. Okay, so now I'm going to do plt dot plot x comma y, and I'm going to also title this plot as y equal to ln x. Okay, so let's first run this. So this is y equal to ln x, but I want this to be one of the 4 subplots. So to that end, what I do is I go and add this command plt.subplot of 2, 2, 1. Okay. So notice that it now looks smaller than what we had earlier. That's because creating space, I mean, it will create space for the other 4, right? So it necessarily has to be smaller than the plot area will be smaller than what we had earlier. So let's go ahead. You have to plot e power x. The interval is 0, 3, right? So x is np dot linspace 0, 3 equal to np dot e. So e power x is np dot exp, right? So np dot exp of x, that will give you e power x. So let's plot x comma y as equal to e power x. Again, let's draw plt dot subplot of 2, 2, 2. This is our second subplot, right? Like we are plotting it here. Okay, so let's run it and see. Okay, so this is ln x, this is e power x. So first row of our subplots is kind of done now. Okay, let's now repeat the whole process for sin x. Sin x is between 0 and 2 pi. So x equal to, so let's make it plt dot subplot of 2, 3. X is between 0 and 2 pi, right? So 2 into pi is np dot pi. Just like you had np dot e, you have np dot pi for the constant pi. Y equal to np dot sine of x, right? So all these things are, you get used to it as you keep practicing, sine, ln, log, all these have to be, you have to add np dot so that you get the respective functions. Okay, so plt dot plot x comma y, plt dot title equal to sin x. Okay, so that will add third subplot. Okay, 1 period of sin x. That is what it is. And finally, for completeness sake, let's finish what we started. 1 by x. So here something interesting will happen. So between 0 and 5, in place of 0, 5, p dot subplot, we are doing 2, 2, 4. Okay, and we are doing 1 by x. Okay. So plt dot title equal to 1 by x. Let's try to plot it and see what happens. Okay, so that nothing came out here. So we have a warning here. So there's a runtime warning, divide by 0 encountered. And when you try to divide 1 over x, right? So someone was pointing out earlier, right, that can we
plot
move?
is missing.
Sorry. Okay.
PLT dot
Sorry.
plot is missing.
Okay. Actually, give us x, but it will still throw the runtime warning. So it's a warning, but still we have to be aware of the warning. Why it's happening? It's happening because x equal to 0, right? So that's what the array begins with, right? So one way to fix this is, instead of starting from 0, we could slightly, stretch it a bit and say start from say 0.1. You get the plot, but you don't get the warning as well, right? So these are small things that will be good to keep in mind.
Sir, like
Yeah.
right now we are plotting 2 by 2. That means 4 plots, and if we want to increase, we can do by 3 by 3 or 4 to 4. So that many subparts will be creating, right?
Correct. Yeah. So you could also do something like, say, it need not be a square, so it could be 4 cross 1 cross 1, if I'm not wrong. So let's try that. I haven't tried that. So 4 cross 1. If you do 4 cross 1, then you will get something like this, right? Of course, it looks horrible, but still, you can do it. In principle, you can do it. Right. So sometimes you might want to do it if there are an uneven or a non-square number of plots, then you'll be forced to do something rectangular in nature. Right? So that ends the second collab. Any questions?
Yeah. What did you say about 1 upon x?
So 1 upon x.
So how did the
Yeah, just 1 second. That 1 upon x, the problem is you encountered, so NumPy encountered a 1 by 0 operation, right? So when it tried to divide 1 over 0, it threw an error, not an error, a warning. So one way to sidestep that warning is to start your interval from 0.1 rather than 0. Okay, so that is the point I was.
For adding grid lines into the plot.
Okay, so I'm not sure. We'll have to search, right? So you can. There are few things. What we are doing is like a very basic intro to Matplotlib. These are things that you can search and find out, right? So there is a way to add grid. I think it is plt.grid. I'm not sure. So there is. We have to search and see.
Excuse me, sir.
So yeah, it is plt.grid, but you have to
make
it square and all that. Yeah, I think you have to do it for each one, if I'm not wrong, right? So you'll have to do it for each one of these, right? So that way you can.
Excuse me, sir.
Yes, yeah. Yes.
Yeah, sir. What if we want to plot the graphs one after the other?
One on top of the other, or
like one after the other. Like first we plot the y equal to ln of x, and then we plot the y equal to e of x, like that, like one after the other.
on the same plot you are saying?
No, sir, not in the same plot, but like first we plot the first graph, and the next in the just after the first one. Not on the same plot. Different plot.
So that's what you have done, right? You mean to say something that is
No. Not
You
this
have
way.
to do 4x1 plot.
No, sir.
subplot.
Like if we do four by one, then the size is like kind of reduced.
There is no getting around that, right? Unless you make it bigger by increasing the size of your figure itself, right? So instead of 8 cross 8, maybe if you do it as say 15 cross 15 and try to plot it sideways, it might work, right? So okay, so any
So
I
I
think
think if we cut down the plt dot subplot line, that will do the purpose.
okay, so that please you can I think try it out. Okay, so these small experiments, I think it's best to. Is that fine? Because can save some time on.
These things we will play around with it.
Yeah,
Sir?
please do that, right? So
Sir?
yeah.
So, like, how did you get rid of the warnings?
Warning, we got rid of that warning by starting from
Semicolon.
0.1 instead of 0, right? If you start from 0, you'll have to divide by 0. If you start from 0.1, you will kind of escape that
Being 0, okay.
0.
Sir. Excuse me, sir.
So we'll unfortunately we have to move on, right? So any questions?
Yes, sir. Sometimes we see figure and axis rather than PLT. What does it mean?
Yeah. So actually, I also haven't understood that properly, right? So what I have presented to you is a very vanilla version, whatever works for me, right? So I also am aware of this. There are multiple ways to do the same thing in Matplotlib, and if I happen to figure out what these things are, I'll let you know. But I also get confused a lot when it comes to there are different ways to do the same thing, right? So same line plot y equal to x, you can plot in say 3-4 different ways, right? So for the discussion, we just stick to this one of the simplest ways that we have seen. Okay, so that also I leave it to your exploration, right? So this is more of an introductory workshop.
And
All right.
you used $sign in title.
Yeah. So that don't worry about it now. That's more of a LaTeX thing. So it's not like really important. Okay, so we have to move on now. Let us.
Are we going to cover all these six sheets today, or on like the whole workshop? In the whole workshop, you will do only these six.
I want to do all 6 today, but let's see. Let's see how much we are able to do till 7 and take it up from there.
Okay.
Okay, so now we come to the idea of a matrix, right? So let's import. Okay, we are connecting to the collab. Okay, so what is a matrix in NumPy? It's again very similar to a vector. That's also an array. So let's go ahead and define it as a list of lists, right? So it's like in Python, you have a list of lists. That's how we define matrices. And it's very similar. That only thing is that you will make it a NumPy array instead of keeping it as a list of lists. So we are one bracket extra here. So that is okay. What is this? Comma is missing. Okay, so that's a matrix. So you have created a matrix in NumPy 1, 2, 3, 4, 5, 6, 7, 8, 9. You define it as a list of lists. That's all you have to do, and you have a matrix to work with. Okay, so I'll rush through this because the ideas are very similar to what we saw before, right? So whatever we can do with vectors, similar things we can do with matrices, right? So 1, 2, 3, 4, B is A6 and 8. Again, I have list of lists. A plus B is C. C 6, 8, 10, 12. Okay, so that's adding two matrices. Scaling a matrix. Let me not waste time here. Let me copy this same matrix. If you scale it, you just multiply it by 3. Scaling is done. 3, 6, 9, 12, 15, 18, 21, 24, 27. Okay, so very similar to what we saw for vectors. Element-wise multiplication of matrices. Again, need to do the usual multiplication. This is again the Hadamard kind of product. A is this, B is A6, 7, 8, and C is A into B element twice. Just use the usual star symbol and you're done. Okay, so all that you saw for vectors, again, as I said, will hold for matrices. So let me just go with this matrix. It's minus 1, 2. So, 1, 2, minus 3, minus 4. So this is the matrix and call it A. So you have to apply this absolute value function on each of the elements of the matrix, right? So f of minus 1 will be 1, f of minus 3, 3. So absolute value function is np dot abs. Right? So if you apply it on A, it gets applied element wise. Okay, so you want to square each element, then let's take the help of A. Let's just change things here. So this 1 square root of 2, so it says np dot sqrt of 2, and we have np dot sqrt of np dot sqrt is square root. Okay, another just like np dot sine, np dot log, np dot cos. This is just define, and all that you have to do for element wise is a square. Okay, so 1, 2, 3, 4 is what you'll get. So far, I think should be familiar because we have not done anything different from what we did for vectors. Okay, this is the first new thing. So call it M here. M is 1, 2, 3, 4, 5, 6. M dot transpose, again, there are two ways to do it. One using a NumPy method called np dot transpose of M. So if I run this, I get 1, 4, 2, 5, 3, 6, the transpose of M. Alternatively, what we could do is we could do just M dot capital T. Okay, again, so in terms of a convention, we will follow the second one and not the first one because it is closer to how we write mathematical symbols. Okay, so M dot T is very close to M transpose. Okay, so we'll stick to this and not use NP dot transpose. Just like what we did for dot products, right? We did instead of NP dot of A comma B, we did A at B. Likewise, here we are going to do M dot T instead of NP dot transpose. Okay, I hope that is clear. So what we have is matrix multiplication. It's occupied, I think, one full week of Python course. And if you see how easy it is to multiply using NumPy, probably be cursing. Go through all that for loops. So this is where you actually see the power of NumPy, right? So if you remember which week it was, week 4 or week 5 of Python, we used 3 nested loop. I mean 3 loops, right? One within the other, and we had to write a whole lot of code to find the product of 2 matrices. And in NumPy, all that we need to do is use this at symbol, right? So that is one obvious power of using NumPy. Okay, so what you have done for a matrix could be done for matrix and a vector. Nothing changes. So you have 1, 2, 3, 4, 5, 6, and
If it is n cross n matrix, then we use multiplication sign, and if it is m cross n matrix, then we use @ here. Is it that?
no, star sign is used for element-wise product, right? The Hadamard product. So if you want to do this, right? Where you want to multiply, yeah, then you use star. If you want to do matrix multiplication, then you use at.
Okay.
So can we summarize it like scalar multiplication and the square multiplication can be done with the star, while
Scalar
doing the matrix
multiplication.
dot multiplication will be using this dot.
Dot product and or matrix products, we will be using at. Okay. So C equal to AX. Yeah, you can go ahead. Yeah.
Both matrices
So,
are not.
sir, here for matrix multiplication, we can't use np dot dot, right?
Okay, so I'm not really sure. Let's try. There is np dot matmul, if I'm not wrong. So there is an np dot matmul which will give you the same thing. Okay, so np dot but let's see. No, it works, right? So maybe let's look at the specification of np dot. NP dot does what? Dot product of 2 arrays. So it just says arrays in general. So they could be so nice, right? So look at the doc string. So if A and B are vectors, that is 1D arrays, it is just the inner product or the dot product. Okay. So if A and B are matrices, it is matrix multiplication. Okay. So NumPy docs itself is saying that matmul or A at B is preferred, right? For whatever reasons of efficiency, they are preferring A at B. If A or B is a scalar, then it is just equivalent to scalar times matrix, I suppose. And then there are ND arrays. ND arrays, we'll come to that in a minute, but let's not go there, right? So I think your question is now answered by this. Is that
Yeah.
fine?
Thank you, sir.
You
Yeah,
can
got your
use
point.
np dot dot, but preferable to use A at B because it is closer to math, simply because it's closer to how we write mathematics.
Okay, so yeah, got it.
A and B matrix should be of same order, right?
Right. Yeah. So if you change it, then you will get a. Let's try to change it so that. The error that we get. Okay, so here it's sorry. I should have added there. Okay, so you get a value error, and this is what it will give you. Right, there is a mismatch in its code dimension 0. Right, so basically it's a dimension mismatch. So n cross k cross m, size 3 is different from size 4.
So defining it, you have put extra comma here.
I didn't get the question.
So while defining it, you have put extra comma here.
Oh, right. Yeah. Sorry, that's wrong. It should not be there. Okay, but you will get a value error if you if there's a dimension mismatch. That is the point. And AX, see, AX is very important because any linear model in ML, you will have to do AX at some point of time, right? So you'll have to do some W transpose X or some kind of W X in the case of neural networks, right? So somewhere or the other, you will be doing this. So this is critical. Okay, so just like you had for vectors, you can define a matrix of zeros. All that you need to do is you need to specify what shape it is. In this case, it is a 2x4 matrix. So NP dot zeros. NP dot zeros of 2x4 and it is. One small catch is that instead of a tuple, if you just say np dot zeros of 2 comma 4, you'll get an error. Okay, so dot zeros requires you to enter a tuple or just a number. In this case, if you just enter 4, it will give you a vector of zeros. If you want a matrix of zeros, then you have to enter the shape as a tuple. Okay, so that is this is again similar.
No, sir.
Let's just
The
copy
shape
this.
in the vector and shape in the matrix is the
So
same.
do it.
Hello?
So we'll come to that. Okay, so we'll come to that. Can you just give me? I'll just change my internet connection. Am I audible now?
Yes, sir.
Yes, sir.
Okay, thank you. So yeah, I'll come to the shape business in a while. Let's quickly go over identity matrix again. Identity matrix, you just have to use a new function called np.i. So the I stands for the I. Okay, so the I of identity, and you get your identity matrix. Okay, so these are things that you just need to remember. It's not too complicated. You just have to specify, since identity matrices are square, you just need to specify the one of the dimensions, right? The other is the same. So if you specify 5, then you will get across 5 identity matrix. Okay, diagonal matrices, again, very useful. We have a separate function for that called np.diag. You just need to pass the diagonal elements as a list, right? So if you do this, you get your diagonal matrix. Okay, so finally we come to the shape and dimension. So the shape so matrix like this, the shape is nothing but what we call the dimension in the usual mathematical sense, right? It's a 2x3 matrix. That's what is the shape. The dimension is going to be 2. Okay, again, I'll as I told, I have to do this at a later stage. Matrices are 2-dimensional numpy arrays. Okay, vectors are single-dimensional numpy arrays. So one way to think about this is matrix has a row concept and a column concept, right? So there are 2 dimensions in that sense. The vector doesn't have, it has only a row or a column, whichever you want to call it. It has only 1 dimension, whereas a matrix has 2 dimensions. You can look at it from top to bottom, left to right, whereas a vector, it's only left to right or top to bottom. Okay, so that is what we mean by dimension. shape is more of the the mathematical dimension, if I may call it that.
So just yeah. So can I read this? Hello.
Sorry, yeah, go on.
Just come to the earlier page, sir.
Yeah.
Yeah. Can I read this array n as it is a 2 feature and each feature have a 3 dimensions? Can I read this like this?
Yeah, you can. So you can read it as there are two samples in your data set, each having 3 features. That is one way of reading it, right? So other way of reading it is there are 3 samples in your data set, and each sample has 2 features. So depending on how you define.
We read it d cross n, mean feature
Correct,
into number of sample.
Correct.
It is a 2 feature, each feature having in 3 dimension plane.
Yeah, that is right. So for those who did the earlier MLT course, I think we used n cross d. For the most recent run of the course, it is d cross n. So it will be 2 features and 3 samples. Okay, so I'll very quickly summarize. There's nothing new that we have done here. We have 2 matrices. The translation from math to NumPy is straightforward, as we have been saying all along. A plus B is A plus B, A Hadamard B is A into B, AB is A at B, A transpose is A dot T. Identity is this, diagonal is this, zeros and ones are very similar. Okay, so that is all we have with respect to matrices. So any questions?
Yes, sir. I have a question. When we do like matrix and vector product, so the vector has this, like if we in terms of matrix, if we think vector is like let's say in the example we have did x equal to 6, 7, and 8. So the shape is like 3 cross 1. And then for the matrix A, you have did like 4 cross 3. So shape are different, but still we are doing add at x and we're getting the answer.
That is because they are compatible, right? So here A is what? Here A is 3 cross 3, right? And
Yeah.
X is what? X is 3. Okay, so they're compatible. If A were to be 4 cross 3, let's say adding one more 10 cross 3, then it's still compatible, right? A is the last dimension of A and the first dimension of X. They should be equal for matrix multiplication to work.
But like sir, the x looks like it's 1 cross 3.
Yeah. So yeah, that's a valid point. See, there is actually no concept of row vector, column vector in NumPy. Okay, so strictly speaking, there is only a 1D NumPy array. Okay, so when you say A at X, NumPy will internally know how to treat X, right? You can for now think about it as it's kind of treating it as a column vector, right? So your confusion is valid.
Yeah, like sir, had it been like a matrix, if x had it been a matrix, then we have to the care about the shape, right?
Had X been another matrix, yeah, you
Matrix,
have
yeah,
to,
like 2-dimensional array.
correct. Then you have to make sure that the first dimension of that X matrix is equal to the last dimension of A.
Yeah. Okay.
So any other question?
Sir, we are getting np dot zeros will give us the whole matrix with the containing 0 elements, and np dot ones we will get the whole matrix containing one element as one. But if you want to generate a matrix of dimension 500 into 500, and we want all the elements to be 5 or 7 or something, can we do that?
Yeah, we can do. Can you think of how you'll do that? So you want 500 cross 500, right? So let's say 500 cross 500. So you want everything to be 7. So how will you do that? Not zeros. I mean, should be.
We can multiply with 500 by generating ones, np dot ones.
Yeah, that is.
Okay. Got it.
So we'll stop there'll be a hard stop for matrices here because at least I want to at least visit the fourth. This will give some kind of completion to the first half of the session. So this is a small collab. Okay, this is a small collab. So we'll try to complete it in 10 minutes, and then those who want to leave for the cloud computing workshop can leave. And then I'll discuss with the others who are present if they want to extend it beyond. So that we'll talk after 10 minutes. Okay, so let's quickly do part. The ND arrays come later. So import NumPy, we want to import matplotlib. Pyplot as PLT. We also want to do some parameters, configure some parameters. Figure size is going to be 8x8, and the font size is going to be 10, okay, or 15. What I kept. So okay, so NumPy provides a way to generate random numbers. So the numbers are not really random; they are pseudo random. So let's see what they are. Let's see how to do that. It provides what is called a random number generator (RNG). np.random.default _ RNG. Seed equal to 1001. Some seed. So I'll just explain what this means. So let me generate some random number in RNG.random. Okay, it generates some random number. Now there is this notion of what is called a seed value. So whenever you fix the seed, the sequence of numbers generated remains the same. So if I run this again, I'll get the same 0.612. No matter how many times I run it, I will get 0.612. Now the moment I drop the seed, say I drop the seed, you'll notice that every time I run this, I get a different random number. Okay, so that's why this is called a pseudo random number generation. Right? So not really random in the sense that there's no way of generating truly random numbers. They are pseudo random numbers, and the moment you fix a seed value, you can kind of say it's the sequence of random numbers that you will get. Okay, so what we are going to do in this collab very quickly is to take probability distributions, generate samples from it, and visualize them using a suitable plot. Okay, so
Sir, can we change the seed value also?
Seed value you can change. Yeah, if you change the seed value, it will give you a different sequence of numbers. Okay, so the way to generate Bernoulli is one of the ways is we do use what is called a choice method, right? So think about a probability experiment. How do you generate a Bernoulli sample? You toss a coin, right? So let's say 0 and 1 are the two sides of the coin, and you are going to toss the coin with probability 0.3. It's a biased coin.
Yeah,
0.3 for 1 second. I just finished this part. So 0.3 for tails, 0.7 for heads. Okay, and let's first try this and see if it works. So this time it produced 1. Whenever times you run it, it will produce only 1 because you fix the seed value. Yes. Mute. Someone is.
Yeah, sir. Hello. Sir.
Yeah. I'll come back to you. Right. I just finished this and come back to you.
Yeah. Okay, sir.
Okay, so this is one example. You have tossed a coin once. Now, if you want to toss the coin 10 times, you say that the size is equal to 10. Okay, so you have tossed the coin 10 times and you have got 3 ones and many zeros. Let's toss the coin 100 times. You will get 100 such outcomes, right? So one way to see if what you're doing is right is to see the shape of x. X is a vector of length 100. Okay, so there are 100 coin tosses. What we want is 1000 coin tosses. So let's. Okay, so we have this. Visualize this and see what it looks like. It's a sea of zeros and ones. All of them are coin tosses. Now delete this and finish the bar plot and come back to the question. So one way to visualize a Bernoulli sample is to do a bar plot. So PLT dot. So before you do a bar plot, you need the counts of zeros and ones, right? You need how many zeros and how many ones. So let's use traditional Python to do this. Number of ones, zeros. Look through x dot shape. Okay, so in this case I know that it's 1000, so let me fix that's 1000. If x of I is double equal to 0, then increment zeros. If x of I is ones.
Sir,
so
I think 1 should be equal to 1 here.
which line?
The line number 2.
No, brother, both of them are variables.
Here counts, right? Counters.
Oh, okay. Sorry, sir. Sorry.
Yeah. So the bars of my bar plot, the heights are going to be zeros and ones, number of zeros and number of ones. My x-axis is going to be 0, 1, right? The simple bar plot is x-axis. Do it in that variable. So corresponding to 0, I want to have the bar. I want the height of the bar to be zeros. I want the height of this one bar to be 1. Now let's plot it and see. Okay, so we roughly have 300 and 700, right? That's what we want. Where Bernoulli is 0.7, p equal to 0.7. 70% of the time you will get heads and 30% you will get tails. Okay, one small thing is the x-axis is kind of crowded. Okay, I don't want so many values on the x-axis. I just want 0 and 1. So one way to fix this is x ticks. Okay, so if I do suppress the output for you. So if I do x ticks of 0 and 1, I'll only have 0 and 1 on the x-axis, right? So that is your bar plot. Let's title it as of 0.7. Okay, that will kind of feed the bar plot summary of our data. Yeah. Now for the question someone asked.
How to put the numbers on the bar plot saying that this much number was 1 and this much number was 0.
You mean this is 300 in that sense, or?
No, maybe on the bar or over the bar.
You want to write here that there are 700 ones and 300 zeros like that? Is that what you want to do?
Yes.
Okay, so that is something.
Legend in the bar graph, no, sir? Like that he wants it.
Oh, is it? I am not aware of it. Let's try. I am not sure. This is, I think, something you can explore, right? I am not sure. I haven't done this. Okay, so you don't have a handle to put the legend. So see, this is something you have to explore. But there is a plt.text. Okay, so see the collab itself and see. So you can position your text here. So let's say 10, 10, x, y. You need to add, say there are 700 ones. We have to verify, but I'm not sure if this will work. You have to explore this, but it is going and adding it here. So you see the 700 ones, right? You have to probably lift this y-axis a bit and say y-axis. So you get the idea, right? So if you want to add text onto your plot, you'll have to do it using plt.text.
Right, plt.text. Okay.
You have to play around with this. Yeah. So
how to read line number 10? I mean, how to
how to express it. Line number 10.
What we are saying is plot give me a bar plot where my bars on the x-axis refer to 0 and 1 and the heights of these bars are zeros and ones. So for example, so let's can someone mute, so there's some noise. The person who is asking the question, then it's fine. If it's someone else, kindly mute. There are 293 zeros, right? So your height of the 0 bar is 293. That is what we are saying here.
Sir, can you please explain line number 11?
Okay, so line number 11, what it's doing is, if you don't have line number 11, then what's happening is there is a default, what do you call this? This is called ticks. Okay, this is called ticks in matplotlib. What it does is it is going to add labels, or not labels, it's going to add tick marks. Okay, so remember in school we used to do this, right? So we used to mark 0, 1, 2, 3 on the x-axis. They are called tick marks. Now, if you don't specify these tick marks, matplotlib will do whatever it wants, right? It's, for instance, it's doing minus 0.25 to 1.25. Now, what I'm saying is this is a bar plot, and I'm not at all interested in 0.25, 0.5, and all these values. I am only interested in 0 and 1. So you please display only 0 and 1 tick. That is what I am asking matplotlib to do. That's what plt.xticks does. So plt.yticks will do something similar to your y-axis. So if you say just give me 0, 300, 700, then it will comply with that request and just have 0, 300, 700. Okay, that's the use of ticks.
Excuse me, sir.
Yeah.
If our data is not binary, then what code should we use for the line 10? Like 0, 1 we
Yeah,
have
it's a good
mentioned, right?
point. So yeah, if our data is not binary, it's categorical, right? So say it's a die. Then what you will do is you will do this kind of biased. Let's say you have a biased die, which is having 0.1 for 1, 2, 3. 4, 5, 6, it has, let's say, 0.2, 0.2. What should be the last one for it to become a probability? 4, 5, 6, 7, 0.3, right? So first of all, I'll generate these samples. So this will be a roll of a die. So let's say I generate this, it looks like this. Okay, so these are the outcomes of your experiment of rolling a dice. Now, what you will do here is, instead of 0, so 1, 2, 3, 4, 5, 6, and you will have, let's call it a list of, instead of zeros and ones, it will be a list of size 6, right? So 0 into 6 will be this much, and then you can just go ahead and implement each one appropriately. So let's just do it now itself. So if I don't want to write 6 if conditions, is there a simpler way to do it? Does anyone have a simpler way to do it? But you get the idea. I hope you get the idea. So there'll be 6 bars and there'll be 6 heights corresponding to these 6 bars. That is how you do it. Okay, so at this stage, I think we are kind of overshooting. So for those who want to leave and attend the
Sir,
cloud computing workshop, you can leave.
yeah, yeah. Sir, actually in a Stats 2 course, we were given some task of performing Monte Carlo simulations of some distributions.
Okay.
Okay. So here, what you have done here for Bernoulli, is it the same kind of thing?
Okay,
kind of
Monte Carlo, I think you would have done it for integration, right? Is that what you did it for? Integration, finding
no,
the
no, not for
integral.
no. We did it for
Okay.
this cost, means tossing a coin or similar things like
Okay.
in stats too.
Okay, I'm not sure. I'll have to look at that before I can comment confidently.
That is
We have
for
seen that for the calculation of the parameter.
From
So yeah, just one question now. Now, those who want to leave for cloud computing can leave. How many of you want to? So there are like few more items in this collab. We'll have to look at Gaussian histograms and then scatter plots, and then there are.
So if we leave this, then we are supposed to go through this YouTube link and do the rest ourselves.
Do the rest. Yeah. So my question is, how many of you want to complete 5 and 6 today? Because tomorrow it might be tough. How many of you want to complete it today, and how many of you?
Let's complete it today because if tomorrow is going to be tough, then.
But sir, we are leaving and then you are going to do that.
Yeah, I will be doing it not right away. I think maybe we can resume at say 8 o'clock. How many of you are fine with that? If you are fine, please let me know. We'll
No, sir.
8 o'clock.
Complete it now.
Yeah, can we do it tomorrow actually? Tomorrow we have it as a second session. So we can
No.
extend.
Yeah, I can do today, sir. No issue.
Let's do it today, sir, because tomorrow will be a heavy
Sir,
session.
tomorrow.
Yeah, tomorrow is not possible because
We can do today.
Today we can do it, sir, because
Okay, if
there will
we
be good continuity of learning.
okay.
But the
in
people
that
who are
case,
leaving for the Microsoft
I
will
agree.
actually lose out.
True,
no,
They'll
you won't
have
lose
to do
out
it
because you will
watch it from
that see that if you are talking from the attendance point of view, attendance is only 2 hours, right? So
I'm not talking about attendance point of view because that was one suggestion also, sir, that if somebody is attending on YouTube also, will the attendance be counted?
it won't be, but see, attendance for this session
Basically, attendance is not the point, no, sir. If somebody is able to do the work, like the assignments, and they are able to clear the OPPE, I think attendance should. Somebody might be looking at it through YouTube later on, if they are busy at this point of time.
Yeah, that's what I'm
So
saying.
more
What
importance should be given to the assignment and the OPPE, I think.
Actually, we can do it tomorrow as well because we have like after tomorrow's workshop there is nothing scheduled for Azure.
No. See, tomorrow I won't be able to do it. So, and besides tomorrow, we already have 2 sessions. You have 4 hours of workshop for MLT, right? So,
Right.
Let's do it today
tomorrow's
only, sir.
Today do
yeah.
it, sir.
So, yeah. What I'm requesting is, can we all break and rejoin at 8 o'clock? We'll keep this.
Yes, sir.
Yes, sir. Yes,
We'll
sir. No
rejoin
issue.
at 8.
We'll Yes, join. sir.
Okay.
That will be better
Yeah.
because I'm actually in my office doing extra, so I can go home and then start by 8 o'clock.
Okay. All right. Okay. Thanks.
That is
Then that is it. So
Yes, sir.
agreed
8
that
is fine.
Yes, sir.
yeah. So we'll rejoin at 8.
Same link, sir.
Link, sir?
Same link.
The
Yeah,
same link?
We'll have the same link.
Okay,
Yeah,
we'll
same link.
rejoin at 8, sir.
The link is same for all the days, I think.
Yes.
Okay. Yeah. All right. Then. This will keep streaming. Those who want to rejoin, please rejoin at 8.
Okay.
Okay. Thank you. Thank you.
Thank you, sir.
Thanks for the session, sir. It's very
Thank you,
good.
sir, for the session.
Thank you, sir.
नहीं
अंकिता
सब बन जाएगा, टेंशन नहीं लो, सब बन जाएगा। या म्यूट क्यों नहीं?
Hello, am I audible now?
Yeah.
Yes.
Okay, thank you. So it's the same level of volume, right? Or should it be louder?
Oh, okay.
Okay, so which screen have I shared? It's the sampling Bernoulli, that screen, right?
Right.
Okay. Okay, so let's continue. So we were looking at this collab. The whole point of this collab is to introduce you to two ideas. One is sampling from distributions, and the second part of it is how to visualize whatever samples you have. So depending on the kind of distribution you sample from, you will have to use different kinds of plots. So for the case of Bernoulli and say categorical random variables or distributions, you have to say use the bar plot, right? So we just saw this, and Bernoulli can very easily be generalized to categorical by adding more number of by increasing the support, right? By widening the support to say instead of 0 comma 1, it could be some x1 x2 till xn, right? So and corresponding to that, you'll have to change the probability values, right? So these are nothing but this is nothing but the distribution, right? The PMF. So the P specifies the PMF of your distribution, and size is the number of data points you wish to sample from your distribution. Okay, so you want to generalize it to categorical, you should in this bar plot you'll have to change the number of bars to n, and you have to find the frequency of occurrence of not just zeros and ones but other values in your support, right? And nothing else changes, right? So this the code is same, it can generalize to any categorical random variable. Okay, so that is the bar plot on the Bernoulli. Now next is the Gaussian, and natural second step from there. Of course, there are other distributions, but from an ML standpoint, Gaussian is important. So go ahead and sample. So if you remember, I'm going to rewrite this RNG in every cell. You don't need to rewrite it if you define it once, but just for it to sync properly, I'm rewriting it. So you have some seed value, let's say 1001, and the mean of the random variable is the mean of the distribution is 1 and variance is 4. So what we are going to do is if you notice it suggests, Colab itself suggests that look, LOC is nothing but the mean, right? LOC stands for location, it stands for the mean. Scale stands for the standard deviation. Okay, so we have to specify the mean and standard deviation. So it will be 1 comma 2. Okay, so it will be 1 comma 2 in our case, and we want to sample 10,000 data points. So let's call it X as usual. Once you sample, you have to always verify if your shape is correct. It has resulted in 10,000 samples. Also go ahead and quickly see how they look like. So since it's not going to display all 10,000, it has displayed first 3 and last 2 here. So first 3 are like this, last 2 samples are like this, right? So that is, we have now generated a Gaussian, a set of samples from the Gaussian distribution, and the choice of plot is going to be histogram, right? So how will you do this? It's very straightforward function again, plt.hist. You have to specify x. You can just stop at that. Let's see what you get. Okay, so you get, press the output and just look at the plot. Get something like this is not bad, but there are 2 arguments that you can add to the histogram to control the output or how the output looks like. So one is the edge color. If I say that the edge color is black, instead of getting this sea of blue here, the edges will become black. Okay, so the edges of the bars, individual bars of the histogram or the bins, they turn black. Okay, so this is better, at least aesthetically, I find it better than the previous one. The other thing that you can control is the number of bins. So by default, it has, I think, 10 bins, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? By default, there are 10 bins. Control that. Say if you want 100 bins, then look something like this, right? So it depends on your use case. So if you add more number of bins, then you'll get kind of a normal distribution. I mean, it gets closer to at least from the visual picture, right? You kind of see why this comes from a normal distribution with mean 1 and variance. Of course, you can't say what the variance is from looking at the plot unless you have multiple plots to compare with, right? You can get some sense of the variance, but anyway, so the bins controls the number of bins, right? So by default it is 10, so we can stick with that. So plt.histograms are very simple. You just need to pass the sample or the data set, and you need to specify the number of bins if you want control over that. Edge color equal to black is something that you do so that you can differentiate between the different bins. Okay, so that is Gaussian followed by the visualization, which is histogram. Okay, often in ML, what we'll do is we'll we'll work with toy data sets, and toy data sets typically are in R2, right? They are in the 2D space, and when it comes to 2D space, one of the most common distributions that we go to are the is the bivariate Gaussian, right? So bivariate Gaussian is just the two-dimensional generalization of the normal. There is some noise. You can mute. Can you mute in case you are not muted? Okay, so how do you generate this? First thing is, I hope you all have seen bivariate or multivariate Gaussian, but if not, instead of a mean scalar, you will have a mean vector. Okay, so this is the mean along the x-axis and mean along y-axis, if you want to think about it that way. And instead of the variance, you will have a covariance matrix, right? So covariance matrix will have the variances of individual directions, variances along the individual directions in the diagonal, and the off diagonal elements will be the covariances between these two values, right? So this off diagonal element, it's a symmetric matrix, the covariance matrix. So the off diagonal elements will have covariance between a pair of features, right? If you want to think about it in the ML sense, this is the covariance between a pair of features, and this is the variance along the first feature and variance along the second feature. You can think about it that way. And this is the mean. Okay, so let's first take vectors out of these. So vectors and matrices. So mu is the mean vector. Covariance matrix is another array. Only thing, it will be two-dimensional, right? It will be a two-dimensional NumPy array. So 1005, or could have also done it as NP.diagonal of. Okay, both of them work. Let's stick to the previous one. Now, once you have this, you use the same random number generator. Remember that when it comes to sampling, you have to use the random number generator. Okay, so RNG dot. Can you please mute? Requesting all of you who are not yet muted to please mute. Okay, so RNG is what? RNG is the same random number generator, but instead of bivariate, we actually have something general which is called the multivariate normal, right? So if the multivariate normal is just the n-dimensional or d-dimensional extension to the single univariate Gaussian, right? So instead of scalar, it's a vector. Now bivariate is nothing but the two-dimensional case of the multivariate. Okay, so that's just 2D version of the multivariate. So you have to specify the mean and the covariance matrix and the number of points that you would like to draw from this distribution. Let's say we are interested in drawing 1000 as given here, right? So let's call this X. Since it's a matrix, let's use capital X. Okay. So if you look at the shape of this matrix, it will be 1000 comma 2. Okay, so 1000 comma 2 means there are 1000 data points and each of them is a vector. So first component of the vector is the x-axis, second component corresponds to the y-axis. Okay, so if you want to visualize or if you want to look at what one of these vectors would look like, it will be something like this, right? So this is how it looks like. Once you have X, the best tool you have to visualize this kind of a data set is using the scatter plot. Okay, so scatter plot, you just need to do something like this. So you have to specify two things: the x coordinate of all the points and the y coordinate of all the points. So for now, stick to this. I'll tell you why we are doing this, what and why it should even make sense. In the next collab, we'll discuss indexing of NumPy arrays. At that time, it will become clear. Okay, so this is how the scatter looks. So the mean is 1 comma 2. So 1 and 2. That's where the center of this Gaussian is, and then the points are distributed around that mean with some covariance. Okay, so that is scatter plots, and there is one change that we can do. So we have to try to zoom out of the plot. At this level of zoom, the structure of the distribution is actually not visible. So what we are going to do is we are going to zoom out. One way to zoom out is to set the limits of the x-axis and y-axis. So x-axis is now from say -2 to 4. What we'll do is we'll make it -10 comma 10, and y-axis also we'll make it. Y-axis is already -4 to 8, so let's make it. Let's now plot this. Okay, so you now see that some shape is coming out, but still there's a problem in terms of the axis being unevenly scaled, right? So this is from -20 to 20. So what we'll do is let's make it 20 to 20 on both the sides, and then we see something interesting happening. Finally the shape comes out. So can someone tell me what I mean by this shape? You see what this shape actually is?
Because of the covariance.
Okay, so because of the covariance matrix, so why is this part longer than this part?
Y has got higher covariance.
Okay,
The
so Y has
y-axis
got higher
is
variance.
most of the information.
Right. So the variance is higher along the y direction. So that's why this is elongated. So it's actually an ellipse, right? If you think about it, if you draw the contours of the bivariate Gaussian, it will be an ellipse. So let's just play around a bit with the covariance and see how it looks. So if we make it identity, meaning 1 1 0 0 1, and if we plot it, if we plot this, you'll see that it is more or less like a circle, right? Because there is the same variance along both directions. So if you make one of the axis 10, let's say now the x-axis is 10, then you'll get an ellipse which is like with the major axis along the x-axis, right? So it looks something like this. Now if you could also now introduce some covariance and see what happens. Let's say it should be a valid covariance matrix. Let's see. If it's not, then it will throw an error. In this case, it happened to be a valid covariance matrix. You see that if you add these covariance terms, then there is some kind of correlation between your x and y, right? So here there's a weak positive correlation. If you notice between your x and y, there is This is the covariance, and you can compute the correlation, and you see that slightly tilted. Let's now try say something like -3 and -3. Okay, so if you try -3 and -3, then there is a weak negative correlation. Okay, so this is how you try to understand your bivariate Gaussian by plotting. Mean is kind of straightforward. It just gives you the location, but the covariance matrix is quite rich and can actually tell you a lot about the geometry of the distribution, and also some information on the relationship between the features, right? That ends this collab. Any questions so far?
So in covariance matrix, do we have that 1 by n term?
Yes, right. That's kind of built into the covariance matrix. So 1 by n sigma xi transpose is the covariance matrix. If
That
you
is
have a
already
data set.
built in.
That is the built-in part, yeah.
Okay.
So here what we are doing is we have the covariance matrix and we are drawing from it. So this is like the population covariance matrix, right? So if you were to estimate the covariance matrix from this, then that's a different issue, right? Here you already have a mean and a variance and a covariance matrix, and you are drawing samples from it. See, now that you ask,
I thought you have defined that COV equal to np dot array. So you are actually making that covariance matrix as 1005. In that way, I thought, shall I use the 1 by n term or not?
Okay, no. So this is like the population covariance matrix, right? So you are, but you ask a good question. What we can perhaps do is, if you stick to 10, I'm not sure if this will work, but let's see 1005, the original covariance matrix in question. And if I were to estimate it, right? So if I were to estimate it from the sample is X, right? So X transpose X by N is not this. So you have to subtract the mean. So I'll explain certain aspects of this code later on. So access, all these things will become clear when we do the next set of next collab. So don't worry if you don't understand this. So if you do something like this, right? So number of data points is x dot shape of 0. Okay, I'm missing something. Am I missing?
Bracket after 0.
Okay, so what do we get? We get 10 -2 -2 1. Okay, so let me have to run this part again. Okay, so you see what's happening here, right? So it's 1005 roughly, right? So what you said is the sample covariance matrix, which you can estimate from the sample. That will be, it depends on the number of points you take. So if you take more than certain number of points, then or the greater the number of points you sample, the closer will your sample covariance matrix be to your population covariance matrix.
Got it, sir. Got it. Clear.
Okay, so yeah, but this is a nice question. So we just add one cell here. This sample. Okay, so where is this used in ML? I hope you all know that whenever you are assuming your data to come from a Gaussian, then you'll have to estimate your model. Especially in generative models, you are going to assume several things, right? So one of the modeling assumptions could be that your class conditional density is Gaussian, right? So in Gaussian naive Bayes, for example, you are going to assume something like this, right? So this is where it will find its use. Okay, so any other questions? If not, we'll move to the fifth collab. Okay, yeah, so we are moving to the fifth collab, probably the most important one from NumPy point of view. Okay, so let's move on to NumPy arrays, right? So far we have been looking at vectors and matrices, and we didn't really talk about what this array is and what properties it has and so on. But this NumPy array is actually the concept which unifies both vectors and matrices, right? So let's go ahead. Right? So this is a vector, call it a NumPy array of dimension 1, and this is a matrix. But as far as NumPy is concerned, this is just another NumPy array whose dimension is 2, right? It's a 2-dimensional NumPy array, that is all. So all the methods that are available for x will also be available for y. So that is the shape. So x is 3 comma m is 3 comma 2. Okay, so that's the idea of an array. And just like we have single dimensional and 2-dimensional arrays, we also have 3-dimensional arrays, right? So this is a 2 cross 2 cross 3 array. So maybe tough to visualize it. Let's go back to our drawing board and see what this really means. Okay, so a single dimension array is clear, right? So this is shape 3 comma and number of dimensions is 1, and there is only a row here, okay, or we could call it a column, but a row seems more appropriate. Now a 2-dimensional array will look something like this, right? So there is the idea of a row cross column here. So these are 2 rows and there are 3 columns here. Now a natural extension of this is a 3-dimensional array. Okay, so a 3-dimensional array will look something like this. You have 1, 2, 3, 4, 5, 6. Okay, so on the front face, but you also have 7, 8, 9, 10, 11, 12 on the back of this, right? So by back, I mean these cuboids, right? So which are immediately to the back of 1, 2, 3, and 4, 5, 6. They are now represented as gray values in brackets, right? So these are actually behind 1, 2, 3, 4, 5, 6. Okay, so this will have shape 2 cross 2 cross 3, where the first dimension is the depth dimension. Depth is like going into the board or into the screen. Row cross column is the same thing. Row is bottom, column is horizontal. Okay, so is this part clear? This is like a 3D NumPy array.
Sir, if you can correlate with the conventional thing that we have learned in MLT, that is feature called sample d cross n, in that term, then will be good for us.
Yeah. So that is there in the next slide, right? So I'll come to that. So very roughly, it can be thought of. You can think about this as images, right? So images of size 2 cross 3. So this is a 2 cross 3 image. There are 2 such images. So there are one image is there in the front, another image is there in the back. So that is the data set you're looking at.
How will the dimension be 3 in the third case?
The dimension is, the row is along this, right? So the row cross column remains the same. So it is 2 cross 3. Depth is the first dimension here. That is 2. The depth is in. Yeah. Okay, so
it is 2 images we are studying. Each image have 2 features, and each feature can represent by 3 points.
No, so 2 images is correct, but each image has 6 pixels, right? So 2 cross 3. So actually, we don't have features as yet. Features have to be extracted after that point, right? So currently you don't have features, but you can think of them as raw features, right? So the pixels are raw features. So there are 6 raw features. Only thing is that they are not in a space. They are not in a linear sense. They are in a rectangular sense. Okay, there is some spatial information. A 2-dimensional information is available to you in structured data like tabular data, right? So you don't have this kind of spatial information, whereas in unstructured data like images, you have some spatial information which you can exploit. Okay, so that is ND arrays. So whatever you do for 2D arrays, 3D arrays, it will extend for any dimension. So the same matrix you can view as a matrix, rather a list of matrices. Okay, so just focus on that term. So
if we consider n-dimensional array, okay, so that is basically a tensor, right? When we
that is a tensor, yeah, it's a tensor.
Okay.
Right. So in the next in the deep learning workshop, I don't know how many of you have registered, but there you'll be considering tensors. These are all tensors, right? So you will be dealing with them much more.
I have a question. Can you go back to the slide where you were explaining about two images depthness? Yeah. So if you see the second image, so let's say like I suppose this is a dimension for the image, and this dimension is in the form of pixel.
Right.
Let's say. So how to describe it? 1, 2, 3, 4, 5, 6. So one image is fine, front image and back image. If I talk about the third image, right? I mean third figure which you have given in the slide.
Okay.
So how to describe this first image where like we have these two rows 1, 2, 3, and 4, 5, 6 value in terms of pixel. Right?
In terms of pixels, so actually you won't have 1, 2, 3, 4, 5, 6. It will be more. It will be like values between 0 and 255 typically, right? So if you have an 8-bit image, it will take values between 0 and 256. So each pixel will be in this range, and the pixel value denotes the intensity of the image, intensity of that particular pixel. Right. So 0 means black, and 255 means white. So anything between that will be a gray value. Is that what you're asking?
So that is fine. So we have selected the value out of 0 to 256.
Okay.
So anywhere 1, 2, 3, 4, 5, 6 is that value. But my question is how to visualize these pixelate if it represents some image.
Okay. So in NumPy you can visualize, for example, this particular image itself, right? So you can, if you assume this is anything like an image, you can say take this thing, right? 1, 2, 3, 4, 5, 6, right? Now if I call this some image, so this is a NumPy array, right? So I can do plt.image. Let me check. So plt.image.
Sir, I am show.
I am show. Thank you. That is the. Okay, so there's some option for grayscale. Do you remember what that option is?
So CMap equals to gray.
So yeah, CMap equals to gray. Okay, what is there? PLT is not imported. Okay, yeah. Now you don't want to import it there because it's only for this particular cell. As okay, so it will look something like this. The first image will look something like this. So may not make any sense to us, but as far as the system is concerned, this is how that image will be. Okay, is that fine?
Yeah.
Okay, so that is the image part of it, and so you could also look at it as this array. So I'll just add this small point here. You started off with vectors using Python lists, right? And then we move to matrices, and there we use list of lists, right? Now for 3D arrays, right? What we do is let's call it a 3D array. We use a list of matrices, right? That adds one more dimension. So list is just unidimensional, list of lists is two-dimensional, and the 3D array is a list of matrices like this. So this will be 3D, and you can just go on and generate ND objects. Okay, so where will this find its use? It finds its use in several places. So let's very briefly look at each ND object and see where it's used. So if you have a single dimensional NumPy array, that's your usual feature vector, right? Which you have seen in classical machine learning algorithms. We say X belongs to RD. That's where you'll be using a one-dimensional array, which is a vector. Where will you use a matrix? You'll be using it in your data matrix, right? So if you have tabular data, structured data, D cross N matrix that you have been referring to in the course, you'll be using that. Or you could also use it for things like unstructured data, right? Like grayscale images. What I showed just now is an example of a grayscale image. Where will you use three-dimensional NumPy arrays? You will use it for, say, an image which has 3 channels, right? So color images. So if you look at any color image, that will typically have 3 channels: red, green, and blue. Okay, so some component of red, some component of green, some component of blue, all these together go to define your image. So there are 3 channels. This will be your depth, and it will be a 10 cross 10 image, right? So you'll be using a 3-dimensional NumPy array there. Where will you use a 4D NumPy array? If you want to consider a data set of 50 such images, then you'll have to store it as a 4D array, right? 50 images, each one is an RGB image of size 10 cross 10 with 3 color channels. So that's when you would do something like this. And you can also go on and say that, I will use a 5D NumPy array. When will I use it? If I'm looking at videos. Okay, so video is nothing but a sequence of images. Okay, that's how you record. That's how your video gets recorded, right? So greater the number of frames, better is your continuity in a video. Let's say your video has 50 frames. Each frame is nothing but an image, and that could be a 10 cross 10 RGB image, right? So you will have 5 dimensions to your NumPy array then.
Sir, excuse me.
Yeah.
If it is instead of RGB image, we can have the video of a grayscale image.
Yes, yeah. In that case, this color channel will go up.
Yeah, just 10, 50, 10, 10, 150, and 10. Is that right?
Yeah, that's correct. It will just be 150, 10, 10.
Yeah, thank you, sir.
Okay, so this is you can also extend this to, let's say, text data, and in which case you'll have to use different kinds of representations, right? So you could use again, you'll have vectors there because your vocabulary will be some 10,000, let's say, and then you'll have to represent a word using that vector, and the whole process repeats, but they are still NumPy n-dimensional arrays at the end of the day. Okay, so that is the use case for 2D arrays, 3D arrays, and so on. Right, any questions at this stage? Okay, so we'll move on. So reshaping, next is reshaping an array. So again, there are different ways of doing this reshaping. So let's look at a vector like this. So you have 1, 2, 3, 4, 5, 6, right? You want to reshape it. Reshape meaning you want to, in simple terms, let's say you want to convert the vector to a matrix, right? For whatever reasons you want to do this. 2 ways of doing it. Okay, one is what is called row major or the row first, right? So I just do 1, 2, 3, and then I move 4, 5, and 6 here. Okay, I do the row first. Or I could do it in a column major fashion. I could do 1 and then 2, 3, 4, 5, 6, right? I do it in a column wise way. Now, by default, NumPy uses this row major order. Okay, so let's go back and do this. You are reshaping this to different matrix. It doesn't matter. So you have a vector, and we are reshaping it as in this command x dot reshape of, and you have to give the dimensions, right? You want it to be a 3 cross 2 matrix. Okay, let's run this. So you see that it has done it in a row major fashion. So 1, 2, and then 3, 4 go in the second row, 5, 6 go to the third row. Okay, so there is a way to make it column first also. If you use term, I'm not sure it's order or order. So if you use order, then notice that you get 1, 2, 3 on the column, first column, 4, 5, 6 on the second column. Right? F stands for Fortran, the old language. I think in Fortran they used to do this column first ordering. What NumPy follows is the C ordering by default. So it stands for C, language C. And this is the row-wise ordering. So by default, it will follow the C ordering. Okay, is that clear? This is reshaping a vector to a matrix. Okay, so you could do 2 cross 3, doesn't matter. Only thing you have to keep in mind is that the dimensions should be compatible. So if it is 6, then you can only do 2 cross 3, 3 cross 2, 1, right? So you can't do 4 cross 2, for example. So if you do something like 4 cross 2, it's going to throw a value error. You cannot reshape 6 into 4 cross 2. Okay, so that is shaping a vector to a matrix. Likewise, you can do matrix to a vector. So you start with a matrix like this. Okay, again, this is the default ordering. Push the rows first, right? So 1, 2, 3, and then 4, 5, 6, and not 1, 4, 2, 5, 3, 6. Okay, so same rules apply here also. So you can start with 3, 6, and you reshape it as 6, right? So what you get, if you change the order to Fortran ordering, then you get 1, 4, 2, 5, 3, 6. If you use C, then you get 1, 2, 3, 4, 5, 6. And C is the default ordering, so you can just drop this and say that I'm going to reshape it this way. Okay, so you don't need to stop here. You could continue and try to reshape matrix in general. So let's try to reshape this matrix into a 2 cross 3 matrix. So let's do 2 cross 3. So let's do 3 cross 2. Okay, so that's how you reshape it. But there's one catch, or rather one convenience here. Let's say for some reason you don't know what the second dimension should be. You know that you need 3 cross something, but you don't know what the second dimension should be. NumPy allows a way to actually do this. So you use the unknown dimension to be -1. Then it will automatically figure out what that is. Okay, so it works both ways. Whichever dimension is unknown, you could just replace that with -1 and it will figure out what to do. Okay, so this is one of the features of reshape which you have to remember.
Sir,
here suppose we have a n dimensions. So in that particular case, -1 we can put any one place. We can't place more than one place.
Yeah, we can't do multiple -1 because it will not have a context to.
Even if the 10th dimension.
Yeah.
Okay.
So 3 cross 2, right? So again, one use case for
sir,
this.
what is the case -1, -1? So can you repeat it?
-1, -1, NumPy cannot handle because it can only take in one unknown dimension. Right? So you see the way it's going to do it, right? So this is a 6. There are 6 items to be reshaped, right? So 2 cross 3, so 6. So if you specify one dimension is 2, then NumPy what it will do is internally it will compute 6 by 2, and it will say that this -1 corresponds to 3. Okay, so this computation NumPy will do. But if you say both are -1, then it won't know what to do.
Okay, sir. Got it. Got it.
So one use case for this, again, I'm going back to images because it's kind of easy to explain, reshape the use case using an image. So again, think about the MNIST dataset. I don't know the current MLT. I don't know how many of you have seen the MNIST that often, but if you have also done a bit of MLP, I think you would have seen the MNIST digits dataset. So there are, let's say, 10,000 images. Each image is of size 28 cross 28. Then if you want to run a classical ML algorithm, or even let's say simple neural networks, what you'll have to do is you'll have to reshape your image into a simple feature vector, okay, a unidimensional vector. So in that case, what you'll do is you'll do x dot reshape of, one dimension, that's the number of images, which is 10,000. The other one you can just say is -1. So NumPy will figure out that it should be 28 into 28, which is 784. Okay, and this is your usual data matrix. You can apply any kind of ML technique on top of this now. Okay, is that clear? This is the use case for reshaping, one of the use cases.
Can you please repeat?
Here is the 10,000 dimension array.
Oh,
Is it?
no, this is a 3-dimensional array. In terms of dimensions, there are 3. It's a volume, right? So whenever you see a volume like this, it's a 3-dimensional array. Only thing is that it's there are 10,000 images.
10,000 items, like 3-dimensional
exactly.
arrays.
Yeah, you have 10,000 items, each of size 28 cross 28.
Okay.
And
those 28
typically,
cross 28 into 784 multiplied 1.
Yeah. Right. 28 into 28, NumPy will do internally because you have added this -1 here. We are reshaping this into a 10,000 cross 784 NumPy array. Okay.
But is there any relation between the number of the volume of the 3-dimensional array?
But is there any?
Like anyway, we have the 3-dimensional array. So in this we have 28 cross 28 and 1. So we wanted to convert the one feature vector, 784 feature values.
So why we are doing this is we want a data matrix, right? Typically what we have seen is most of the algorithms that we have studied take a data matrix of size n cross d or d cross n as input. So what we have here on the other hand is a data volume, right? It's not a simple matrix. So we need to somehow feed our algorithm data of this form. So that's why we reshape. Right? So that's the blue thing, right? So everything that is blue is now kind of stretched out into one horizontal blue column here. Yeah.
Single row.
Yeah.
Yeah.
Okay, shall I move on to one more important part? This is matrix vector addition, right? So if you have a matrix like this 1, 2, 3, 4, 5, 6, and you want to add a vector to it. Okay, so let's say it's a row vector. Now this is kind of easy to visualize, right? So you add 1, 2, 3 to the first row, you add 1, 2, 3 to the second row, and you get the result. Okay, so can we do that in NumPy? Yes, we can. Let's quickly see how it's done. 1, 2, 3, you have 4, 5, 6, and you have the vector as 1, 2, 3. So all that you need to do is m plus b, and you're done. You get.
Is it kind of broadcasting?
Yeah, this is again broadcasting, right? So your 1, 2, 3 is broadcasted. It's as though stretched in the other dimension by another 1, 2, 3, right? So just like you had, where did we do this? So when you try to multiply, this got stretched by in this direction. What's going to happen here is that this is going to get stretched in the downward direction, right? By 1, 2, 3 again. Okay, so that is what is happening here, roughly.
So similarly, like it can happen along column also, right? It happened this time, like it happened across the rows, right?
it happened across the rows. We'll come next to the
Yeah.
column, right? So we'll see why there's a problem when it comes to columns. Okay, so let's look at this. So we want to add this column to all these three columns so that it becomes 2, 6, 3, 7, and 4, 8. Right? That's what we want. But here is where there is a problem. You cannot. So the way you have written it, right, or the way you see it, it cannot be stretched down. Okay, you can't stretch it down because the shapes won't match, right? You can't stretch it to the right, you can't stretch it to the down. There seems to be some problem with this idea of stretching it because the dimensions are not compatible.
I have a query here.
Yeah.
So rather than looking at it 1, 2 horizontally, can we look at vertically?
Okay, so this is where I'm going to kind of slightly introduce this idea that a NumPy vector, right? Vector something like np dot array of 1, 2 is kind of treated as a row vector. Okay, so when I say np dot array of 1, 2, so this is again only conceptual. NumPy kind of treats it like a row vector. Okay, so what I have to do is I have to convert it. If I want to add it to the columns of the matrix, I have to convert it into a row, into a column vector, and I do it like this. So it is originally having a shape of 2 comma. Now it will have a shape of 2 comma 1, right? So let me go and run it. Okay, so it's the same vector of it is 1 comma 2, but then earlier it was treated like a row vector by NumPy, again conceptually. Now it has become a column vector, and now I can allow to add it to. Okay, now if you see, it will be what we want: 2, 6, 3, 7, 4, 8. Okay, so let me erase the whole thing and show you what happens if I just add m plus b. Okay, so this is one of the rules of broadcasting, which I earlier mentioned. Okay, you can't broadcast these two together. 2 comma 3 and 2 you cannot add together. This is one of the rules. So if you try to add 2 comma 3 and 2 together, this stretching won't happen. Okay, so for it to happen, you have to necessarily reshape B as a column vector, and then if you add, you'll be able to add. Okay, so this is
So basically that means for a array of dimension 1, the transpose also gives that dimension 1 only. It's
Yeah,
only so that's why you have to reshape array of dimension.
Sort
to
of.
get it to a
So,
column vector.
yeah, to get it into a column vector, yeah, you have to do this kind of reshaping.
Right.
Right. So there is another way, but I don't want to confuse by adding that. There is it's called expand. So you basically expand each dimension by 1. Currently, it's just a vector, right? 1 dimension. So this also has the same effect as reshape. It will make it 2 cross 1. You expand the number of dimensions of B by 1. So I mean by 1 in the sense you make it 2 comma 1. So if I do 0, then it will do it as 1 comma 2 or a row vector. I don't want that. So I wanted to expand it and make it a column vector. So to do this also. Any questions here? This is kind of slightly tricky concept. So questions?
There are one question, sir. Transpose, why not transpose work on the single dimension? If it is work, then I can also say that B dot transpose.
Okay, so I don't have a proper answer to this. All that I can say is that for one-dimensional arrays, there is no concept of transpose. Right?
Okay.
So it only comes in. So what you can do is you can go look at the docs. So the docs, they mention, I think they very nicely mention it. So for a general array, right? So for a general NP array, transpose you kind of reverse the whole thing. So for example, if your have 4 dimensions, and transpose will do something like B comma C comma B comma A. Will kind of reverse the whole thing. Okay, so if it is 2 dimensions, what happens? A comma B becomes B comma A, right? In terms of dimensions alone, I'm talking. So if
Right.
it's a 5 cross 3, it becomes a 3 cross 5 matrix.
Right.
So the extension of this apparently is reversing the dimensions totally for an n-dimensional array. For a 1-dimensional array, therefore, it will remain A comma, right? There is nothing to reverse here.
Okay. Okay. Got it.
Okay, so yeah, so one way to remember this column vector, row vector business is, if you want to add this is the recipe that you have to remember. If you want to add a row vector to a matrix, you can just do m plus b, it will work fine. If you want to add a column vector to a matrix, then you need to do this business of reshaping. Okay, this is a recipe for now. In case you don't understand the broadcasting, because we haven't really explained it. So this is the recipe to follow. Okay, row vector means simply add, column vector means reshape and add. Right, so that is the part about index reshaping. Now come to again a very important part, which is indexing and slicing a NumPy array. It is quite simple. So if you want to extract the third row of the matrix, right? So third row here is 5 comma 6. All that you need to do is 1, 2, 3. Okay, so let me just introduce one more thing to you so that nice practice for reshaping. Let's say I have a list of size 10. So this is a Python list of size 10. You can create a matrix out of this, an array out of this. Okay, so this will be a vector. Now, if I want to get this kind of an object, what I need to do is I need to reshape this as 5 comma 2. Is that right? So I need to reshape this as 5 comma 2. If I do that, I'll get what I need. Right? I don't need to keep doing this 1, 2, 3, 4, 5, 6 business every time. Okay, so it's a nice trick. I hope you all followed this. Okay, so now we have this matrix. How do you extract the third row? Just need to do m of 2. Okay, you will get the third row. If you want a column, I'll take a list of numbers. So this will include 1 to 9. Take I press something. Okay, I'm sorry. Where were we? Yeah, so we were here. I reshape this as 3 comma 3. So I have a NumPy array of 9 and I reshape it 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and I need to extract the second column. Second column is actually something like this. Okay, so you understand what I did now? So if you have not looked at NumPy before, here or are there any confusions here? Okay, so what I have done is colon corresponds to a floating dimension, right? So what I'm saying is when I add the colon, I mean everything along that particular dimension is allowed. Okay, so I'm not fixing it to anything. So I'm not saying that it should be 0, 1. So m of 0 comma 1 will be what? Number 2, right? M of 1 comma 1 will be the number 5. M of 2 comma 1 will be the number 8. So what I'm saying is I want all these numbers, right? I want the entire column. So instead of putting a specific value, I'm just replacing it by a colon. Okay, so this is how I extract a particular column from a matrix. Yeah, I could do the same thing for the row. For example, if I want the second row, instead of doing m of 2 alone, I could do this. It also works. So this is the third row. Second row would be something like this, right? So what we want here is the second column. So I leave the row part empty and index into the column alone. Okay, so that is the column slice. Now let's go and do the submatrix slice. Just like you have row and column slices, we are also NumPy also allows you to take a matrix itself as a slice.
So just a minute. Is this what you had done in the scatter plot when you were presenting it? I think, was it same thing about slicing itself where we took plt.scatter x just a colon
Exactly.
and 0?
Yeah. Right. So I'll get back to that. Right. Maybe I'll show that now itself so that where is the scatter? So that's what we did in the scatter. So thanks for pointing it out. So let's go to the scatter. Okay, so when we did PLT of x colon comma 0 x colon comma 1, all that we were doing is we were taking the first column of x and the second column of x. So let's the shape of x. Okay, so the shape of x was 1000 cross 2, right? So there are 1000 rows and 2 columns, and the first column corresponds to x values, the second column corresponds to y values. So how have I plotted all along? By passing the x values as the first argument and the y values as the second argument, right? So we need to pass the first column and the second column. This is how we do it, right? So thanks. So that is the column slice. So that's the use case for something like the column slice, right? So if you want to do a scatter plot of some data matrix, you could do it this way. Now for the submatrix slice, so let's again take a list of numbers. It's a range. So this will be just the Python list from 1 to 16. We'll create a NumPy vector out of this list. Okay, that NumPy vector will be.
We can do also np.arange directly.
Yeah, good point. Yeah, let us take that. So
yes.
Thanks for pointing it out. So this directly gives us, as Kumar has mentioned, what we are looking for. Now we can just reshape this, turn it into a 4x4 square matrix, right? So that is M. So what we want is the second and third rows. So let me 0, 1, right? So 1 is the index of the second row, and similar to Python's list indexing, I want to go till the third row. So the index has to be 3, right? 0, 0, 1, 2, 3. The last value 3 is not included. So this will translate to 1 and 2, rows 1 and 2. And column should be 0, 1, 2, 3. So it should be 2, 4, right? Since 4 is like the last index, I can just leave it as it is. That will give me 7, 8, 11, 12. Okay, is it clear what we did? This is slicing at its.
Come again, sir.
Okay, so let me just do one at a time. Let's say I just do 2, So let me just do a list kind of a setup, right? So 4. Yeah. So this is just a list, right? So list of lists. So 5, 6, 7, 8, 9, 10, 11, 12. I get the 2 rows starting from M of 1 and M of 2. M of 3 is not included because usual Python indexing conventions. Now in this row, I want these 2 columns. So I do 0, 1, 2. So let's say I want only the second column. It will look something like this, 7, 11. But I also want one more column. So I do 2, 2:4, right? So I get 7, 11, 8, 12. But since there are only 4 columns, I don't need to add this. Python will understand. Is that clear now?
Yeah. Okay.
Okay, so it's just usual list slicing, but done 2 times. One for the row, one for the column. Okay, so this is yeah. So we completely forgot use case for. Okay. So any questions so far in the slicing business? All right. So next, again, very important part is how do we retrieve or filter selective elements from the array? So again, a useful feature in NumPy is that let's say I use the array range from now on. Okay, so it has 0 to 7. So you get this array. So you want to look at all those values at indices 1, 3, and 6. So what you can do is you could sure about the syntax, whether it's a list. Yeah, it's a list of indices. Okay, so you can pass a list or another array itself as an index. Okay, you can pass a list or another array itself as an index. I have passed the indices 1, 3, 6 here, and I get those values in the array which are at this index. Okay, so you can index using arrays or lists themselves. That's the point here. Any questions about this aspect of NumPy? Okay, so closely related is the idea of filtering values, right? So let's say you have this array. Now I want to extract those elements that are positive. Okay, so one thing I can do is I can just ask this question, where all is x greater than 0? And what it will do is NumPy will run this operation element wise and it will return a boolean, right? So 3 is greater than 0, it's true. 1 is greater than 0, true. 0 is not greater than 0, so it's false. Minus 4 is not greater than 0, false. Same for minus 2, 1 and 5. Okay, so when you have some kind of a comparison operator along with the NumPy array, it is going to return a boolean, array of booleans. Now what you can do very interestingly is this itself is an array, right? So you can pass this as index into your original NumPy array, and that will end up getting you those indices where the boolean result was true, right? Outcome of the boolean was true. Okay, in this way, what we have done, we have in just one line of code extracted all the positive numbers from this array.
So will it work on matrix also? Means to 3-dimensional array also?
Yeah. So all these things will. So for example, let's quickly reshape this. How many are there? 1, 2, 3, 4, 5, 6, 7. It's a prime number. So let's just add one more, right? Minus 5, and reshape it as 4, minus 1, right? So x will look something like this. Okay, that's interesting. So what is happening is, okay, it's giving us value, but it's not retaining the. Okay, there's no way it can retain the shape, right? It can only give you those elements which are at those indices, right? There's no way it can retain the shape of the matrix, but it still works on the matrix also. Right, you got the point, right? It's going to give you the positive elements, but the shape information will obviously be lost, right, in the process.
How would the list of booleans that is there can look in this case?
Right, can you repeat the question? I couldn't hear it.
Yeah, how will in the previous case, when it was just one dimensional, we saw the list where initially it was booleans when it just satisfied the condition. How would it look in this case?
Okay, here it will be a matrix of booleans, right? So it will be matrix of booleans, and again it's done element wise, right?
Yeah,
So you can. Okay, so this will go and index into your matrix, and wherever it is true, you will get those values out. 3115 happen to be the only positive numbers. And okay, so if we move on, it's like a very long collab. There is keeps going on and on. Okay, but this is important. Any other questions? If not, I'll move on. So matrix vector addition, one use case is there. I think we'll leave it for now. It's used in, say, neural networks, right? So if you have a linear combination of x and w, and typically you add a bias vector, right? So this is where you do matrix vector addition. So you have a matrix of activations or pre-activations or whatever you want to call it. It's not either of them, but some linear combination, and you want to add the bias term to each of these three neurons. Then you will end up doing matrix vector addition. Okay, so the bias is common for these three neurons, right? No matter how many samples you have, you will be adding the same bias to each of the linear combinations. Okay, so this is one use case. Axis, right? So we saw shape, we saw dimension. There is also this concept of axis for a NumPy array, and it's a very important, very useful term. So for a single dimensional NumPy array, the axis is, there is only one axis, it's 0. For a 2D array, you have two axes, right? One is axis equal to 0, which corresponds to the rows, and the axis equal to 1 corresponds to the columns. But usually this row and column are kind of confusing. So the way I look at it is axis equal to 0 is top to bottom. So when you want to move from top to bottom, it's like if you want to sit on top of the array and compress it for whatever reason, that is axis equal to 0. If you want to compress it from left to right, okay, if you want to press it against a wall, then that is axis equal to 1. Okay, so there is also a 3D version of it, and that will look something like this. Axis equal to 0 will be the depth of the 3D volume. Axis equal to 1 will be top to bottom, and 2 will be left to right. But you don't need to worry about this. It's enough if you understand this. Okay. So here is a nice use case. Let me take this. This what? This is the matrix A, right? So the matrix A is 2 cross 4 matrix. 1, 2, 3, 4, 5, 6, 7, 8. So what we want to do is we want to sum the row vectors. 1, 2, 3, 4 is one row vector. 5, 6, 7, 8 is another row vector. So I want to move from top to bottom. So what I do is I do A dot sum along the axis 0. Okay, so I have moved from top to bottom, that is along axis equal to 0. That will result in the sum of the row vectors. I can do something similar for the columns. Instead of axis equal to 1, I just need to do axis 0. I need to do axis equal to 1. I'll get sum along the columns or the column vectors. Okay, so the way to remember this is 0 means top to bottom, 1 means left to right. Okay, any questions about the axis part?
If we leave the mention, if we don't mention the axis, then by default, what does it do?
Good point. So if you don't mention the axis, then it will sum the entire array, entire matrix. In this case.
Okay.
Right. So that is why we mention the array, the axis. Okay, so I'll move on. So there are why is this axis important? Because it allows you to do so many kinds of operations. I have listed down 4 of them. So let's do the range first from 1 to 10. That will be this particular numpy array, right? So what is that numpy array? It's just reshape it. It is standard 3 cross 3 array. So let's do this. We want the sum of column vectors. Column sum. So this is m. There's nothing but m dot sum along axis equal to 1, right? Because I want to move from left to right. That is the column sum. So next thing I want is the mean of the row vectors. Mean, row mean, right? So this is nothing but m dot mean along the axis 0. I want to move from top to bottom. Okay, so this is the row mean, and now I want the variance of the column vectors. So column variance is m dot var right. So I do that column variance, and I want the L2 norm of row vectors. So row norm is I need to do np dot lineage. Remember, this is lineage norm. Now I want the norm of row vectors, right? So I'll do axis equal to 0 because I want to go from top to bottom. Okay, let's take here. I have not specified my matrix. Okay, so the column sum, I hope you get it. It's 6, 15, and 24, right? It's 6, 15, and 24. Likewise, the row mean is also some quantity like this, 4, 5, 6. It's 4, 5, 6 because 7 plus 1 plus 4 is 12 by 3, right? So it's 4. This is 5, 3. Okay, so that's 4, 5, 6. And what else are we printing? Column variance, of course, can't calculate by hand now, but that's how it is. Have we done the row norm correctly?
We should square root. We should add square root, I think.
Okay, norm does the square root, but what is the norm of this row vector? 1, 2, 3 is what? 9 plus 4 plus 1 is what? Square root of 15. Okay.
I guess.
14 is it? Sorry. 14. Okay. I think. Let me just check. This part alone is always confusing for me. So, okay, this is actually. Okay, so the norm here is taken along, so axis equal to 1 corresponds to row vectors here. Kind of makes sense. Do you see why it makes sense?
Similar way, like you were doing the sum. For 1, it was going from left to right.
Yeah, for 1 it was going from left to right, so you are right. So for 1 here, it takes the norm of the vector 1, 2, 3, right? Okay, so did everyone get that part? This is slightly tricky. So you got it, and not, you can play it now. Final part in this collab is how do you stack two arrays? So
Can you please repeat the norm part?
So the norm part is, see, 1, 2, 3 is the, that there's actually a slight difference. I should not have clubbed these four together. Some mean and variance are similar operations in the sense that they aggregate the rows, right, or columns. But norm is not doing any kind of aggregation, right? Or it is doing, but in a slightly different sense. So when you say norm along axis equal to 1, it is taking the norm of these 3 row vectors, right? So it is the norm of the vector 1, 2, 3, which is what the axis equal to 1 forces it to do. Okay, so what?
So if I want to calculate L1 norm, then what can I do there?
So there you will have to add, okay, one norm, you will have to do something like this, right? So I think L1 norm is a simpler example. Let me change this to L1 norm because it will be easy. So focus on this part alone. You are doing np.linearalgebra.norm of the matrix M along the axis 1. So along axis 1 is left to right. So you are considering left to right. In this case, they are row vectors because there's no aggregation happening across these vectors. You are just treating each vector as it is. Okay, and order equal to 1 is for the L1 norm. Does that make sense?
Yes, sir. It is treating as one vector, single vector.
It's treating it as a single vector. Okay, this is slightly tricky. I'll probably revisit this. So add a note in case someone looks at later. So yeah, stacking is, it follows from this whole axis business. If you have A like this and B like this, then you can either stack them one on top of the other or like this. So we have a function called concatenate, which works like list concatenation, but in this case they are arrays. We have to pass the arrays you want to concatenate as a tuple. You want to concatenate A and B together along the axis 0, top to bottom, right? So one way, 1, 2, 3, 4, 5, 6, 7, 8. So this is one way of concatenating. The other is left to right. So let's change this to 1. Okay, so is that clear? That's the end of this collab, and that was a bit too much, but still. Okay, finally we move to the PD plots, and hopefully we'll close with this. Okay, for 3D plots, what I've done is I've already imported certain things. These are clear to you by now. And import matplotlib is also clear. There is one more import for matplotlib, which is a 3D version. So since we are plotting 3D, we'll have to import this also. Okay, so that is as far as the imports are concerned. Now let's look at how we can draw contours of this function, right? So that's what we look at first. In order to do that, you need to understand the idea of what is called a mesh grid. Okay, so mesh grid is as follows. So let's say you want to plot some two-dimensional function f of x comma y, right? Typically, how will you go about it? you will consider a grid, right? So earlier you had this idea of lin space, right? So you wanted to plot a single variable function, so you had to consider a certain number of points on the x-axis alone. Whereas now you have a two variable function, so it's not enough if you just consider one axis, you also have to consider the other axis, right? So you have to specify something like f of 1 comma 2, right? So for that you need a grid, and this is the grid. So the grid looks like this. I have filled in the individual values for each grid. So this is the 0 comma 0 point, this is 1 comma 0, right? So 2 comma 0, 3 comma 0, and so on and so forth. Each cell will have a unique value. This is the x-axis, and for certain reasons I've drawn it in the y-axis. The y-axis as downwards. Okay, so I have this in place. Now let me consider the same grid that I showed you. 0 comma 1 comma 2 comma 3. Okay, 0 1 2 3. Y is also divided into 4 parts, right? 0 1 2 3. Now how do I generate this kind of a setup? We can do this by using a function called mesh grid. Okay, so NumPy does this for us nicely. Okay, so let's look at what x is. It looks something like this. Looks like this 0 1 2 3 0 1 2 3. Okay, if you actually go here, this is what mesh grid is doing, right? It's extracting the x coordinate of each of these cells and putting it into one array. Okay, so np.meshgrid returns two arrays. One of these corresponds to the x part of it. The other one corresponds to the y part of it. So if I print y, you will see what it's doing. It give you 0 1 2 3 0 1 2 3 along the vertical direction, and this is nothing but the y-axis part of the grid. Okay, so if you combine these two together, only then can you define a function at any point in the grid. Okay, do you get the idea of what mesh grid is?
Yes, sir.
Okay, so this is what a mesh grid is doing, and the moment you have a grid like this with x and y, you can now define your function, right? Let's define our function as x square plus x square. So it will be f of x comma y, and that will be my z value. So now I can go ahead and plot contour for this. Okay. Again, the problem is this is not giving us smooth contours. That's because we have only chosen 4 points. So in order to avoid this, let's go back to our lin space. Let's say we are plotting the contours from -2 to 2 points by default. Y is also now try to plot the contours. See that they are nice circular contours because that's the function we have chosen, right? So contour of this function will be what? X square plus y square equal to constant. So it will be circular contours.
Actually, what is the use of mesh grid?
Mesh grid is exactly this part, right? So see, you want your function's value at this point 1 comma 2. In fact, you want your function's value at every point, right? You are plotting, what are you plotting? You are plotting a surface, right? You are plotting x comma y comma z. Okay, so if you want x comma y comma z, you need to know what is the value of z at every x comma y on a grid of points. And mesh grid, what it does is it gives you this grid. It generates this grid for you. So if you give the x-axis values and the y-axis values, okay, as 0 1 2 3 0 1 2 3, it will generate this grid of numbers for you. And
Like
on top of the grid,
pair of values gives the. combination of
it'll
values.
right. It'll give you the pair of values x comma y, every pair of values, right? So 0 0. It'll give you 0 0 1 0, and then you can
Yeah.
evaluate z and plot it. Okay, that's what we have done here. That's what mesh
Yeah,
grid
thank
did.
you. Yes.
Okay, so that is the contour. So let's now extend this and try to plot a 3D surface. Okay, in fact, let's plot the 3D surface of this function itself. Okay, so the f is here, x and y, the x, capital Y are already there. For this, I'm going to introduce slightly new way of plotting. So you are telling your PLT that you need a 3D plot, and you're saying x dot plot surface. You're plotting a surface. You're not just plotting a contour. You're plotting a surface of these two grids, and on top of that z value. Right? Let's just try this and see what happens. Okay, so this is your convex kind of paraboloid, right? So if you rotate a parabola, you will get this around your 3D. There are some options that you can choose. So there is one color scheme called Viridis, right? So slightly better. Okay, so this is one color scheme that you can use. This is how your surface is going to look like, and if you can visualize, if you draw planes parallel to the surface, you will get circles, right? Which is why you have contours like this. Okay, so that's the surface plot. Now let's plot it for this one also. Okay, tell me what kind of what object, mathematical object is this actually? If you think about it, what does it look like?
Exponential.
Okay, exponential is what else does it remind you of?
Fraction.
In terms of statistics, that's true. What is it? It's not exactly something, but it's close to something. So what distribution is it? Close to?
Normal.
Normal distribution.
Is it just the normal or
Exponential, it might be.
Gamma, I think so.
no, normal is correct, but is it just the univariate normal or
It is continuous normal.
is a bivariate normal, right? So
Bivariate.
that is what this is. Let us now go ahead and copy this. It remains the same. So I have to generate a grid again, and I won't repeat this. So other than repeating it, standard. So let's copy this recipe. Okay, so we have here. It doesn't look so good because we have chosen the wrong range. Let's change the range to okay. So there are few arguments, something called the row stride and the column stride. If you change these, your plot might look a bit better. So let me try to play around with this a bit. It's not kind of, it is not perfect, but still you can see that it peaks at -2 comma. Where is it supposed to peak? It's supposed to peak at -2 comma 1, right? So that's where it peaks, -2 comma 1. Okay, so that's the surface plot for your Gaussian.
How you said that it is wrong range?
Okay, so because I already plotted this before, but earlier it was -2 2, right? So this peak is at -2, no? So this will reach its maximum when it's the mean of this, if you consider this like it's not a Gaussian because it's not normalized to 1, but if you normalized it to 1 and if you treat it like a bivariate distribution, its mean is at -2, 1, right? That's where it's peaking. The mode is at -2, 1, then I think the mean is also there, if I'm not wrong.
And what is its R stride and C stride is doing?
So C stride is how much you move in each direction. So for example, you notice that this is coarse, right? So if I kind of decrease the row stride, you will see that they are closer together, the lines. You see it? Like they are much more closer now. If I change the column, then they are, it's more finer. Okay, so that's what they mean.
Understood, sir.
Okay, so
What
this
is the
is,
use of this graph?
sorry?
Where we can use this graph? When by seeing this contour plot, what additionally we can decipher?
By using a contour plot, is it?
Yeah, this surface plot, it's looking is nice, but what
Yeah,
additional information we are getting?
Okay, yeah. I don't think there is any specific info that you get apart from being able to visualize how it looks, and yeah, there is no utility from the ML standpoint as far as I know.
Okay.
Maybe,
Right,
sir,
so
we can visualize the gradient better.
Perhaps.
I have
Sir.
one question.
Sorry, yeah. Yeah, go ahead.
Yeah, yes, sir. Actually, sir, we have given the 1, 1, 2, 2 values or in the mesh grid, but it is continuous. How it has become the continuous, sir?
Okay, so this is actually, it's similar to the lint space that we did, right? So if you remember, we were trying to plot y equal to x square and we use discrete values, but once we increase the fineness of the grid or the fineness of the intervals, right, the graph started looking continuous.
Here, by default, it has taken 50 points.
Correct. Yeah, let's try that. Let's
Okay,
maybe
thank you, sir.
try and see if it's the parameter size or it's something else. What is it? Name of it. Okay, so this is how it looks, right? So very coarse. Okay, the final part is why did we do all this? So that we can try to optimize this using SciPy. Okay, so there are two parts to this. We'll try to wrap it up soon, and that is constrained optimization and unconstrained optimization. So constrained optimization, there are basically just two things that you need to do. We imported the SciPy, right? So let's import this again. It's not needed, but just so that it's all in one place. So from SciPy.optimize, we are going to import this minimize function. And we are going to write the function that we are going to minimize in terms of vector. So x is a vector. So this is a vector. I'm going to call x. I'm going to call this as x. Okay, just a abuse of notation, but x comma y together is a 2D vector in R2. Okay, so now this function is of minus x of 0 plus 2 plus 2 whole square, right? So that is this, and minus x of 1 minus 1 whole square, the whole thing divided by 6. I have to return this, so I need to optimize this function. And usually SciPy is going to follow some numerical algorithm, right? So it's going to follow some numerical procedure. It requires a starting point. So let's say the starting point is 0, 0. and then you call the function minimize on the function that you want to minimize. Starting
Sir,
point.
here it has asked to maximize the value the function.
So you have to do what? You have to return minus of the function.
Okay.
So instead of minimizing, we are trying to maximize, but SciPy only gives us minimize. So we'll try to minimize the negative of this function.
Okay, got it.
Right. So let's store the result in something called result. Result.x will give you the minimizer. Okay, so if you notice, you get the answer as -2, 1, which is where the maximum is. Okay, so -2, 1 is where the maximum is. So this is how you minimize a general function. This is easily can be extended to n-dimensional or d-dimensional functions, right? So instead of x of 0, x of 1, you'll probably be doing something else. Okay, so all the other apparatus remains the same. You can extend it to any number of dimensions. Okay, so this is unconstrained optimization. The final one is constrained optimization. Again, for this, you have to import and minimize, and since you have a linear constraint, you have to import something called a linear constraint. Okay, so let's go ahead and take the function that we want to minimize. Again, x will correspond to y here, so you have to return minus x of 0 square minus x of 1 square. So to maximize, you return the negative of the whole thing. Okay, so x0 is again going to be array of, we start from 0, 0. You start from 0, 0, and you minimize this function f, starting with the initial value x0. One point you have to add, and that is the constraint. So the constraint is given of this, is given like this. So it is given as matrix A times x, lower bound less than or equal to ax, less than or equal to upper bound. So that is how you have to specify the constraint. So it is all there in the docs. I'm just demonstrating it for a simple case. Here A is what? A is just a vector. 1, right? So lower bound, so you notice A is just a vector here. A dot x will be just the A will be the array 1, 1 dot x. X will be x of 0, x of 1. So x plus y, what will be the lower bound and what will be the upper bound? Can you tell me here? What should be the lower bound for this constraint? In case you have been following so far.
1.
1 only.
1 will be the lower bound. Upper bound will be infinity, right? So I just say it's called np dot infinity. That is nice way of saying infinity. So this is the constraint. This linear constraint. I plug in the linear constraint. Okay, so the result of this optimization, I store it in the variable result. And optimal value, the minimizer or the maximizer is result.x. Okay, so there is some error. What is that error? Okay, so this should be equal to. Okay, so it's saying that it's 0.5, 0.5. Says that the maximum of this constraint optimization is 0.5, 0.5. What we'll do is we'll very quickly verify if that is the case by plotting the contours, right? So we'll plot 1 minus x squared minus y squared using linspace and mesh grid, right? So the same process. Let's say -1,
So this
1.
the code above line number 11. What is that? RES.
RES is the result of the optimization. It returns some object.
That's clear.
RES.x is the optimal value, the value at which the function attains its minimum or maximum.
Okay. Okay.
So that is that x.
Please explain line number 8.
1 to x. You want me to explain? Line number 8.
8.
Yeah, so 8 is, so this is actually what? This is, I'm writing this, let me rewrite constraint as of the form ax. So we can rewrite the constraint. As far as SciPy is concerned, I have to rewrite this linear constraint as some ax lying between lower bounds and some upper bound. Right? So this is, he wants, this SciPy fellow wants it to be a dot product. Right? So let me say a dot x. What should be the choice of a? The choice of a should be 1 less than or equal to matrix 1 comma 1 times x, right? So dot matrix x comma y. Is that correct? I need to rewrite this constraint as 1 less than or equal to dot product of a and x between some lower bound and upper bound. This is what I have done here. I have given the value of a as 1 comma 1. The lower bound is 1, upper bound is infinity. Okay, so I have to minimize this function f subject to this constraint starting from the initial point x0. Is that clear now what we have done?
Yes, sir, it is clear now.
Okay, so now let's verify this. So I want to do this mesh grid of comma y, that will give me x comma capital Y, and the function, the z value is f of this mesh grid. Give me the function. Now I can plot the contour of z. Okay, that will only give me the contours. So
Define two variables for the function.
Right. So this should be, this will be the contour, right? Again, this is circular contours, but what we also need to do is we have to plot the constraint. Constraint is what? X plus y greater than or equal to 1. So the constraint line will be plt.plot. What is y as a function of x? 1 minus x, right? So I have to plot x comma 1 minus x. Okay, so this kind of looks ugly. I have plotted the contours and I have plotted the constraint, but I want to change this a bit. So what I'm going to do is I'm going to give specific values to my contours, right? So I want my contours at 0, 0.5, 0.75 and 1. Let's first try that. So you'll have only 4 circles now. Okay, so what? It's not values. It's should be levels. Okay, so these are the levels, not values. Okay, so I have drawn 4 contours now. This is 0. I don't think there's anything corresponding to 0 because this function can be 0, but let's have one more here. Okay, so the contours are kind of there, but it looks elliptical because of uneven axis. You notice this is from -1 to 1. This is from -1 to 2. So I don't want that. One way to do that is to limit your axis. Plt.x limit it between -1 and 1. Do the same thing for the y-axis, limited between -1 and 1. Okay, so what we have now is a 0.25 contour, a 0.5 contour, 0.75 and 1. Okay, and this is your constraint line, which is x plus y equal to 1. And notice where your constraint is hitting your contour. It is hitting it at 0.5 comma 0.5. So everything that is So that point where it hits the contour is going to be your maximum, right? Do you see why it's going to be the maximum? Because your this is going to look like a dome. So let me just very quickly plot this. Very quickly plot this so that you kind of visualize what this looks like. This is nothing but go down. Okay, this is nothing but minus h square minus h square. Looks like a dome, right? It's going to look like a dome, and when you add a constraint saying that x plus y should be greater than or equal to 1, it is everything beyond some region, right? And the dome part, the peak of the dome doesn't come there. So your maximum is going to lie on exactly that part of the constraint which is touching one of the contours. And that's going to be 0.5 comma 0.5. Okay, is this clear what we did? Constraint optimization, surface plots, contour plots. Any questions?
Can we repeat it tomorrow again? Because I think now there is some kind of cognitive load.
Okay, so what I'll do is I'll repeat it on Sunday, because Sunday is when we'll be doing SVM, and SVMs require constraint optimization. So we'll go over this part on Sunday. Okay, because this is what we'll be doing then.
Yes, sir.
Yeah,
That
I have just one doubt in this. I still didn't understand that res.x. How exactly
course.
are we?
Yeah, so see, res is, let's just print res and see what happens. Res is this kind of an object which has many things, right? So it has some message which says optimization was successful, and I think it has some number of iterations and all that. So one of the objects or one of the attributes of this object is the optimum value of the function. What value of x minimizes this? So res.x is the argmax, if you want to put it that way. The argmax of f of x comma y.
Okay,
so
now
that-
it's clear. Now it's clear, sir. So it's just pulling out that particular instance of that object.
So tomorrow who will take?
Tomorrow, Vipin will do regression and regression, and then that will be the second session. The first morning session will be Anamika will handle k-means clustering. Okay, so from tomorrow it will all be ML techniques, and today was like the base for understanding those techniques.
And
Okay, so
the assignment will be mailed to us, or it will be available in the portal?
it will be available in the portal, but it's not the same link. Okay, so we'll add you to that link, that course. So just 1 second, just let me just finish this part. So the last slide is this. I hope that the lesson you have learned is something similar to this, that NumPy is just a lot of math done using Python. Okay, so at the end of the day, that's all it is. And these were some of the references that were used. So I'll upload these slides in that same link. That should be
Which link actually you are talking about, sir? Where I can find that link?
this tiny.cc, right? So this tiny.cc, I shared tiny.cc/mlt_workshop.
Sir, whatever you have taught today, if we want to practice, means you have given a lot of things. I mean, different kind of concepts. Okay, so if we want to practice gradually, means to be expert on these things, what would you suggest? Is there anything we can go there and say, do the practice work?
See, there is one nice website. Could start from that. In case you are looking at where I took the code for 3D plotting from, right? So there is Python Data Science Handbook. The Jupyter notebooks are available, right? So it's a very good. The whole thing is available, if I'm not wrong. So that's where I took all these things. Not all these things, at least the 3D part of it, right? So you can go through books like this, will steadily introduce you to these concepts.
So what would be the pattern of
The practice work only means, is there any online portal where we can go and means do the practice for numpys and all these things, whatever you have taught today?
Not sure if there is any practice portal as such. Best thing would be to implement these techniques from scratch, and in that process you will learn a lot of NumPy. So that's how. So you can look at one of your colleagues, one of your peers, right? He has developed, coded all these algorithms from scratch, and he has maintained a GitHub repository. Okay, so that is the best way.
Okay.
Just for like constrained optimization problems, we can pick up any question in from our course and then try to solve by coding that question.
Yeah, that will be very good. So MLF, you have done a lot of these, right? So you can pick up any one of the MLF questions and see if it works. Yeah, that will be interesting.
Yeah. Thank you.
Okay, then I think it has been a long session. So thanks for joining, and we'll resume
Thank you,
tomorrow.
sir. Thank you, sir.
Thank you, sir. Thank you.
Thank you,
So
sir.
there will be an assignment.
Thank you, sir.
Yeah, there'll be an assignment, but we'll release it soon, right? So the deadline will be next Wednesday. So you have time till then.
Okay. Thank you.
So what the book name you suggested? Python Data Science Handbook, right?
Yeah, Python Data Science Handbook.
But your slide is much clearer than that book. It's make many sense, and that got the many clear the idea.
Oh, right. Thank you.
Thanks.
So, in the case where we give that initial point in the end for minimization problem,
Right.
will it be something similar to where in gradient descent or ascent where we take an initial point and then go over it?
Right.
Does it
Something
work
like
in a
that.
similar way?
Yeah. So see, these are there are many solvers. So there are different kinds of solvers for these problems. So it depends on what solver you use. So you can actually look at the SciPy page. So there is one page for SciPy, scipy.optimize.minimize. Okay, so that if you go to that page, you will see a number of solvers. These are all constraint optimization solvers, right? So they have some algorithmic procedure, and the initial point for that will be this X naught. Something similar to gradient descent, but of course.
Yeah, okay. And in this directly, are we able to get the value of the function also at the end, or do we just input the arguments?
Okay, that is. I think you get the value of the function also. So if you notice.
Yeah, in the res when you printed it, I didn't see the value of the function.
Okay, so see this. You're able to see this screen now?
Yeah.
This res. I think this is the minus 0.5, right? This is the value of the.
Oh, but it should have been 0.5. Right? Okay.
No,
Yeah, we are doing.
Yeah, minimizing, right? So
yeah.
So of that, so that will be.
Okay. Yeah. Thank you.
Okay, so thanks for joining. We'll meet again tomorrow. Thanks, sir.
Thank you, sir. Thank you.
Yeah, it was a wonderful session.
Yeah, thanks a
Thanks
lot.
for putting the effort.
Thank you.